Hello, I'm Jeff Clune. This video will show you our 2019 ICML tutorial on recent advances in population-based search, including quality diversity algorithms, open-ended algorithms, and indirect encodings. And during the recording of our tutorial, the first about 15 minutes were cut off. So what we're going to do is I'm going to redo the intro, then Joel Lehman's going to redo the beginning of his part, and then once we're ready, we'll cut to the original video of our tutorial. So the idea here is to share with the machine learning community ideas that we consider to be very exciting in that they're powerful because they've helped us solve previously unsolvable problems, and they're insightful in some way because they have some deeper insight that can help us not even with these current algorithms but design future algorithms. And also they're very forward looking in the sense that we think that they're not just interesting because they are empirically shown to be quite powerful, but actually that they might help us get to our most ambitious AI goals, including creating artificial general intelligence, which is to say that we think that they offer a foundation upon which we can build future algorithms, that we don't think that they're dead ends in that sense. We also focused on ideas that we think are not very well known in the machine learning community, but are useful to people in the machine learning community. The reason they're not as well known is because they are population-based methods, and traditional machine learning community does not deal with populations of agents, but a single agent trying to solve a task. But we think that the ideas and the algorithms and the insights behind them are very broadly applicable. And they can be used with non-population based methods such as deep learning and deep reinforcement learning, and also that they can be used beyond neural networks. So all the examples you'll see today are with neural networks, but you can use them regardless of your data structure, including if you're using and training decision trees, program synthesis, etc. So we also want to point out that most tutorials introduce a bunch of new methods to the audience, but we also think that this tutorial is fun because it's going to introduce new types of problems that you may be having considered before and that we hope that you'll think of joining us in trying to solve. And that includes two new things that we propose and believe the community should think of as grand challenges. So we'll introduce what those two grand challenges are and hope that you'll join us in working on them. The topics covered are going to be novelty search, quality diversity, then we'll have a brief Q&A for 5 minutes, then we'll do open-ended search and indirect encoding before looking forward and briefly doing conclusions, and then another Q&A session. So I really hope you enjoy it. Next up is Joel Lehman to tell us about novelty search.
Because this is a tutorial on population-based search, it's useful to first review what that means. So the main idea in population-based search, as the name suggests, is to maintain a population of candidate solutions instead of only a single parameter vector, as is more typical in deep learning and deep reinforcement learning. So the field of population-based search asks what we gain from optimizing a collection of parameter vectors together. And we want to acknowledge that for many of you, your existing exposure to population-based search might be simple algorithms like a vanilla genetic algorithm. So if we look at the right, we have this cloud of points that's kind of optimizing over a classical optimization surface. And this is an example of a genetic algorithm. And each of these dots, blue dots, is a member of a population. So the algorithm is pretty simple. You randomly initialize all the members of the population, and you iteratively evaluate them. Then call the ones that are the worst performing and make noisy copies of the better one. And as you can tell from the figure on the right, this is a black box kind of optimization algorithm. You have this convergent cloud of points moving towards a global optimum. And within machine learning, we know that there are many different kinds of black box optimization algorithms. And this kind of convergent search doesn't necessarily make a convincing case for the benefits of a population because the population is all kind of clumped together. And so we want to acknowledge that this might be your perspective so far, and we want to present some really exciting ideas that go beyond this. And so throughout this presentation, we try to make the case for different reasons why populations could be really useful or interesting. So one reason why populations could be really interesting is that they enable you to have a diverse search, a search that's driven by diversity or that has a component of diversity. And this could be useful intuitively because you might want to not have all of your eggs in one basket. You want to be exploring different kinds of solutions. And one thing you can imagine doing is try to take this to a logical extreme and just encourage diversity as like a very central drive of a search process. And this is what is done by novelty search. which is a technique that I'll be describing in this section of the tutorial. And you can view it almost as a philosophical thought experiment as to what would a search process driven only by diversity look like, which is sort of a radical perspective, to have a search that's not looking for anything beyond just to expand out into the space of possibilities. And there's an underlying hypothesis behind novelty search, which is that search algorithms that make diversity a very, very central part of search might be necessary to scale to some of our most ambitious machine learning objectives. And certainly in machine learning, we have no shortage of very ambitious objectives, the most ambitious of which might be to create human-level intelligence. So why might it be the case that we might need diversity-centric search? So we can first begin this question by examining the nature of objectives and objective functions. So within machine learning, we're aware that objective functions are ubiquitous. And for the purposes of this talk, when I talk about an objective function, I'm going to mean a function that measures the quality of a solution. And you might imagine that an objective function implicitly defines an objective to reach. So beyond some threshold of the objective function, you have achieved your objective. And we're also aware in machine learning that objective functions don't always paint a smooth path to finding a solution. There's an issue of local optima. Sometimes objective functions instantiate smooth landscapes that are easy to optimize. And of course, sometimes optimization is more difficult because of thorny local optima. And we can view a lot of the progress in deep learning as making our functional approximators less susceptible in some sense to local optima, although they still exist in certain circumstances. So one question you might ask is, taking into account the issue of local optima, maybe what we really need to do is just to really create more powerful optimization algorithms. Maybe our problems would be solved if we simply created more powerful optimization algorithms. And I want to pose a thought experiment that tries to make the point that beyond just having more powerful optimization algorithms, it's really important what end we drive our optimization algorithms to. And it may be unrealistic to suppose that simply having a more powerful optimization algorithm is going to be a panacea in itself. So this is going to come back to machine learning, so just bear with me for a moment. We're going to kind of first investigate search in a much more broader context. So in machine learning, we investigate search in the context of searching through a space of parameter vectors usually. But search is a really general phenomenon, and is something that we investigate also in science and culture. And so what we'll do now is have a thought experiment in the space of scientific innovation. So for a moment, imagine that you are an inventor in 500 BC. And you have just invented, let's say, an abacus. And the abacus is something that excites you as an inventor because it now enables you to increase the amount of computational work you're able to do quickly. So it's kind of an increase in computational capacity. And you are not satisfied with this. You really have really ambitious aims. So you really want to push this metric of computational performance up many orders of magnitude. So you're in 500 BC, so you don't really know that maybe what you're aiming for is something like a laptop, but you want to have that kind of computational capacity. So imagine you're 500 BC, and you want to get orders of magnitude better on this metric. What should you do? And so what would be most natural to probably try to do, if that was your one true metric that you're using, was just to kind of start with an abacus and try to innovate in this space and improve the abacus in some ways to abacus plus, maybe it has more beads, to abacus B3, that's sort of the best abacus you can possibly get. And probably after that point, you might get stuck, because really what you should be doing in this thought experiment is just doing basic science for a couple hundred years. You might need to get really curious about the nature of electricity. That might lead you to think about different electrical components, and maybe lead you to the space of a vacuum tube. Maybe that would be a really important ingredient that eventually could help you get to where you want to go. So the point here is just that the stepping stones from some starting point to a really ambitious objective, stepping stones aren't always clear from that objective itself. There's nothing in the nature of computation that necessarily points you, if you didn't know about it, to electricity or to vacuum tubes, for example. And the history of innovation is kind of littered with examples of these sorts of serendipitous or unforeseen stepping stones. And the claim is that this is something that happens whenever you have really ambitious objectives. It's called the problem of deception. The idea is that when you aim at really ambitious objectives, the objective function can often become a false compass. The objective function is not going to actually lead you towards the stepping stones you really need to get there. And the way that this manifests is that stepping stones to an objective often are seemingly unrelated to that objective. It's only clear in hindsight that to get from an abacus to a laptop, you might need electricity or vacuum tubes. To get from, in the context of biological evolution, to get from a prokaryote to a human, it requires all these sorts of really complicated innovations like multicellularity, development, and neurons that may not initially have benefits for intelligence, for example, if you want to get something like human-level intelligence. And in our case, in machine learning, to get from a randomly initialized neural network to a highly intelligent robotic control policy, we might imagine that also is a very ambitious objective. We might not get there simply through optimizing a simple objective function. So trying to make the case here, once again, that it's not just that we need better optimization algorithms, we need to think about how we're driving search. So when we talk about ambitious objectives, implicit in these optimization of ambitious objectives is a hopeful assumption that improved performance will lead to greater improvements all the way to success. And empirically, we know that this just doesn't always work in machine learning because of local optima, which motivates things like curriculum learning or reward shaping or engineering, which is sort of a manual approach to try to fix this problem. It's also connected to ideas like intrinsic motivation, like curiosity, and the framework of optimal reward functions. And the overarching issue here is that the stepping stones to success don't always resemble success. You have to do something in addition to optimizing your true objective to get there. So what can we do? One thing we could potentially do is to take inspiration from other search processes, powerful search processes that have innovated and created really complex things. So we might take an inspiration from biological evolution, for example, which has uncovered the vast diversity of complicated, interesting solutions to life's problems. We can also take inspiration from cultural evolution. As scientists, we're aware that sometimes that science has no overarching goal, just as biological evolution has no ultimate organism it's aiming for, and that scientific innovation often progresses by scientists working on their own problems and expanding outwards and creating new fields. So both these are kind of ideas of search processes that aren't necessarily driven towards a single final goal, and it could be that that's key to why they're able to actually create really complicated and ambitious things. So we can take this into account from a machine learning perspective and think about how we can get towards more creative search. So the radical idea that novelty search kind of explores, and so once again this is a section about novelty search, is that can a search that is ignorant of its intended objective sometimes outperform search that's aimed directly at its objective? So can pursuing an ambitious objective sometimes undermine attaining it? So taking this idea seriously, we might need to actually figure out how we can make that into an algorithm. What sort of search pressure could instantiate this kind of more open-ended creative search that would have creative divergent forces? And you might imagine that a population could play a key role here because we need to kind of keep track of all these diverse open-ended possibilities. And this is the idea that motivates novelty search, is to guide a population-based search only by novelty. And so we can kind of think about this first from what the different heuristics are implied by searching for novelty versus an objective. So the objective-driven heuristic is that what improves performance locally is going to be a stepping stone towards greater and greater and even the best performance. And we know in practice that this heuristic sometimes fails. The novelty-driven heuristic is something different, which is that what is novel may lead to further novelties. And intuitively, this sort of makes sense, that a really good paper often will lead to a lot of follow-up work. And one nice thing about the novelty-driven heuristic in the context of population-based search is that even if one vein of novelty kind of runs dry, because you have a population that's concurrently exploring many different novelties concurrently, not all of your eggs are in one basket, and overall, the search may be very healthy and continue to diversify as long as some of those veins are working out. So we can then think about how to actually concretely make this into an algorithm. And the idea is simple, that we just need to change the incentive of search. So you start with a population-based search algorithm, and you replace the standard goal-based objective function with a measure of behavioral novelty. So there's different spaces or ways you can measure novelty. You can measure novelty in the space of parameters, but as you can imagine, that might be an uninteresting form of novelty, that there are many sort of degenerate parts of parameter space. So what's interesting about considering behavioral novelty, so I'm talking about the context of maybe like a robotics domain or an RL domain where you have an agent that behaves in an environment. If you're measuring the behavior of that agent, then actually to be novel, in behavior might require learning something new. And so maybe it's a more interesting form of novelty. So we want to encourage search to kind of discover interesting new artifacts. And that's one reason why behavioral novelty might be a good heuristic for that. And so we replace the standard goal-based objective function with a measure of novelty, and we'll measure that novelty relative both to the current population, where search currently is, and an archive of previously novel individuals, so where search has been in the past. And the idea is that if we are incentivizing new individuals to become novel, then over generations, the search will spread out over the space of behaviors. So also implicit in this is that we're going to have a characterization of behavior in a domain. We have some measure of what behavior means like. And we can actually measure novelty within this space, which is kind of demonstrated in the lower right diagram, using a k-nearest neighbors distance function. So you might say you're novel if you are far from your k-nearest neighbors in this behavior space. So the red dot is more novel than the yellow dots, and the gray dots are at least novel because they're sort of encompassed by everyone else. So this actually instantiates an algorithm, and we can then try it out. And a very simple domain to kind of demonstrate the potential of novelty search is this deceptive maze domain. So imagine you're a mobile robot. You're starting in the big circle, and you're trying to get to the little circle. And we incentivize you from an objective point of view by getting close to the little circle as the crow flies. So this could be a gradient of your objective score. And so you might notice that this is a deceptive fitness function because there's a cul-de-sac, which means you can get very close as the crow flies to the goal without actually reaching it. And there's like a natural gradient of progress. Whereas the true path to the goal, you must first get worse by your objective performance measure before you get better. And this is purposeful. So you might say this is unfair, but this is actually just an example of a very simple domain in which there's a natural deceptive objective function. And the claim is that this is a model of difficult, ambitious problems in general, that we think ambitious problems will have this sort of structure. So we can imagine then, first thinking about what a solution to this task might be like. So just to give you an intuition of what this looks like, here's a video of what a solution policy looks like. It's a little robot that kind of goes through the maze using its sensors. So it gives you an idea of what actually this is. And then we can think about what it would look like to run search in this domain with both novelty search, which is going to be visualized on the left, and objective-based search, which is going to be shown on the right. So in this domain, we measure behavior by the ending point within the maze of a new individual. So in each of these plots, you're going to see new dots pop up. These dots will indicate where a new robot ended within the maze. And so as we run this animation, the objective-based search on the right is going to concentrate its dots in this cul-de-sac because that's where it's kind of the gradient of objective fitness is leading it to be deceived. On the right, even though it's not trying to solve the task in any direct way, the pressure towards novelty is encouraging novelty search to find new behaviors that end at different points in the maze, and it's learning actually how to navigate the maze because over time, to be novel, you have to actually learn to navigate, and it solves the problem, although it isn't even trying to. So the interesting result here is that a search that's not trying to solve the problem, novelty search, actually solves it quicker than a method that's trying to solve the problem. And this is just a philosophical kind of proof of concept of how ambitious objectives can lead us astray. So another domain where we also see a benefit of novelty search is in biped locomotion. So here the objective is to get a control policy for a biped robot that enables it to walk far. So objective-driven search is going driven directly to try to walk far. In contrast, novelty search is going to be incentivized to try to walk to with a novel trajectory. And so it's not directly trying to walk far, but you can imagine that as it kind of falls over in various ways, it might get bored with that and it'll have to kind of walk far in order to become novel. And an interesting part of this is that it may be and that the stepping stones to a robust walking gait don't necessarily directly look like robust walking gaits or might not immediately improve performance with respect to traveling far. So a canonical example of this is that walking requires oscillation, and it could be that just walking in place with an oscillatory motion would be a stepping stone to walking, and this is something that novelty search would recognize, but the objective search wouldn't. So when we run the search, these are the best policies found by objective-based search and novelty search. Novelty search finds a more robust gate that travels farther than the objective-based search. So another example of when not searching for your ultimate objective pans out better. So the claim is not that this always is going to work. It's not a panacea, but it's interesting that it can work at all. And although the results that I showed in the previous slides were with very small neural networks, it also works in a deep RL context. We had a paper at NeurIPS last year using an extension of OpenAI's ES, and a paper in last year's NeurIPS deep RL workshop using a deep GA, also with this Novelty search extension. And there's also, beyond Novelty search, there's also a lot of related work that touches on similar themes, such as autonomous mental development, intrinsic motivation, and curiosity, which is also about agents that are learning not directly inspired by a final objective. And so this is a really interesting body of work, and encourage you to look into it. And we believe what makes Novelty search unique is really the way that it hammers on this issue of ambitious objectives and how sometimes searching for something can preclude you from finding it. These ideas are also starting to percolate in deep RL. So I'm not going to go through all these papers, but one paper in particular that's really interesting is called Diversity is All You Need. And as you might imagine from the title, it has a very similar theme to Novelty search. It's also about just looking for diversity. And it's a really interesting paper. I encourage you to read it. And the premise is basically that you use a multimodal policy, which is kind of similar to a population, and that policy can be incentivized to develop easily distinguishable skills in a sort of collaborative discriminator framework, sort of like inspired by GAN. But it's collaborative as opposed to antagonistic. There's also really interesting work by Pathak et al. On curiosity-driven exploration, where just being curious with no other objective can get you, for example, to progress far in Mario or some Atari games. So also interesting work that's similar, inspired in some ways. So to conclude the Novelty search section, it's really interesting and sort of radical that pursuing that pressure towards creative divergence alone can sometimes outperform directly seeking the objective. And the claim isn't that this always is going to work, and it's actually natural to think about how you might integrate Novelty search with the pressure to achieve. That also a key force in biological and technological evolution is that there is some kind of goal-directed behavior within that. And that's sort of what the next section will kind of start to explore. So while raw novelty can work, it's really natural to try to merge novelty pressure with the pressure to achieve. And there are many paradigms for how you might want to approach this. You could use a weighted average of the objective and of a novelty score. You could use the objective to guide search until you think you've gotten stuck, then switch to novelty, and so on. And what's an effective mechanism in practice, and also highlights another benefit of using population-based search, is population-based multi-objective optimization. And here's the ref there. And the idea is basically to have the population spread out over the space of all possible trade-offs. And so it's nice because instead of having to have a fudge factor that weights the difference between different things, you can, at the end of the day, give to a human user perhaps a spectrum of choices that are just trade-offs. So popular algorithms for population-based multi-objective optimization include an algorithm called NSGA2, which is the one that is used in a lot of the work that we'll be describing here and going forward. And the main idea of these kinds of algorithms is to maintain a Pareto front of non-dominated solutions. So the idea is that A is greater than B, or A outperforms B, only if it scores better, A scores better than B on all of the objectives. So here if we're using, let's say, the objective score on one as one objective and novelty as another, only if you score better on the objective function and on novelty are you truly better. Otherwise, you're just sort of incomparable in some sense. And so if you had a search that's driven by these two objectives and using this multi-objective formulation, then on one side of the Pareto front, you're just only kind of grinding on increasing the objective score. On the other side of the front, you're just trying to discover novelty for novelty's sake. And then the rest of the Pareto curve will represent different kinds of trade-offs. And maintaining this sort of Pareto front is another interesting possibility enabled by maintaining a population. So one issue with the approach as formulated, just having objective score, the absolute objective score on one axis and novelty on the other, is that it's sort of, you're combining novelty with a global competition objective. So in some ways, this doesn't address the fundamental problem of deception, because still on the one side of the pre front, you're just grinding away at increasing the objective score, which is just going to, for example, push you into that cul-de-sac in the maze that I showed earlier. And you might say that this paradigm of global competition embodies a paradigm of diversity in service of progress. In other words, you might think of it as really caring about the objective score as a central guiding principle and just using diversity as hopefully getting away around maybe small local optima. So we can imagine instead having a different kind of algorithm that might give equal priority to both diversity and performance. And so we can kind of take inspiration from biological evolution and think about how what biological evolution isn't looking for one uber organism, but it is finding lots of interesting solutions to various problems of life. And evolution has this quality has this property of niches. And so a niche is sort of like maybe one way of life. And competition is often localized within niches or between only a few niches. So it's not that a bacteria and a bear are competing directly. We can actually explore the potentials, the merits of both bears and bacteria without worrying about them sort of crushing one another. So we might actually have a different idea of a kind of search process we might want to instantiate, which would be to optimize towards the best version of each possible solution niche, as opposed to being kind of always orienting towards the best absolute possible performance. And this leads to the idea of quality diversity, which is a different kind of search process. We want to find the best possible example of each achievable behavior. So it's kind of a different kind of goal. You might ask, why would that be useful? Why would we sometimes want to have a quality diversity algorithm? And the idea is that after you're done running this kind of algorithm, where you have the best possible example of each achievable behavior, what you really have is a repertoire of fundamentally different ways to solve a problem. And you could give this repertoire to a human designer, and it could highlight a wide range of possible design possibilities that they could choose which one they like. It could enable a robot to adapt to new circumstances, which Jeff will talk about later. And it can also help circumvent deception by creating an implicit curriculum. So in other words, solving the problem in one way that's simple might actually enable you to solve the problem in a more complicated way. It's actually better in some ways, but you might not be able to get there without this sort of quality diversity pressure to explore niches for their own benefits. And Jeff will also talk about that later. So this kind of highlights that depending on what you really care about in search, sometimes objective performance isn't the most important factor. Sometimes you want to illuminate the space of diverse possible solutions. And it may be that sometimes diversity in how a problem is solved is more important or interesting than gaining only the single most efficient solution. So coming back to biological evolution for a second, we think of bacteria and bears. From a human point of view, we think both of these are interesting, and maybe actually from a human view, we might be more interested in the bear. But from a evolution-centric point of view, like what evolution is optimizing is ability to survive and reproduce, bacteria are a much, much, much more efficient solution. They take just 20 minutes to get to sexual maturity, whereas bears take much longer, 3 years, and humans take even longer. But because these things are not directly competing with each other globally, evolution provides both of these niches and allows both of them to survive. And we get to see then a much wider range of solutions to life's problems than just simply a convergent process that gives only bacteria. So to illustrate this more concretely in a domain, in a kind of thought experiment domain, we take a domain of virtual creatures. And so in this scenario, we can optimize both the morphology, so the structure of a virtual creature robot, and the controller, the policy that drives that virtual robot. So we might, to motivate this domain, we might say, what if what we want to do is to see the best possible locomotion strategy for all areas of a morphology space. So the pressure to achieve would be to successfully locomote, and the space of diverse possibilities would be in a morphology space. So what do I mean by a morphology space? It's that we might be able to map a particular robot morphology into some summarizing statistic about it. So maybe the height of the robot and the mass of it and how many active joints. And so we can take a robot and map it into the space, and we could say then concretely what we mean by having the best possible locomotion strategy for each of these different niches in morphology space. So this leads us to consider the novelty search with local competition algorithm. So the algorithm I presented earlier had this idea of global competition, where you just had on one axis of your Pareto front just global absolute objective scores. And so what's going to happen here is this is going to favor niches with higher capacity for objective performance. So in our morphology space, it might be sort of those that live in the cheetah-like area of morphology space. And we might not see then interesting solutions to other parts of morphology space which are just harder to eke out good locomotion strategies, but might yield interesting designs that we still might want to see. And one solution to this problem is the idea of local competitions, that we want to explore niches relative to their local capacity for performance. So instead of having a absolute objective score, we create a relative score. We ask how many of your morphological nearest neighbors do you outperform? And that gives you a relative score of how locally you compete. So to kind of revisit that diagram, what novelty search with local competition does is has novelty on one side of was one objective in this Pareto-based population-based search, and on the other axis we have the local competition score. How well do you compete against those that are most like you? And when you run this algorithm, and we create a heat map of the kinds of morphologies that are discovered by different kinds of search processes. Here, each dot, here what's shown are two dimensions of the morphology space, height and mass, and the darkness of a square indicates how strong that locomotion policy is relative to the best possible in that niche. And so novelty search finds all these morphologies, but none of them really do anything. The objective-based search finds high-performing morphologies that are centered in a very central band of the morphology space. Global competition, because it has novelty pressure, is spreading out a little bit more, and local competition is giving you both a wide spread in morphology space as well as high-performing solutions that are throughout the space. So kind of this is just showing that the search process does what we think it should do. And then we can also look at videos of what results from just one run of this process. So what's interesting here is that ordinarily search might converge to just one solution, or a sort of small family of solutions. But because we are using a local competition where we also encourage diversity throughout this space of morphologies, we get a lot of different solutions just one run, which we argue is making interesting use of a population. So you get creatures like these, which are sort of in the sweet spot of morphology space. They are things you might expect to see, things like horse-like creatures, crab-like creatures, something that vaguely looks like a scorpion. But beyond these solutions, you also get really interesting solutions that are in very difficult parts of the morphology space, but still are interesting solutions. So once again, from the perspective of building a repertoire, we might be very glad to have these solutions. They might be useful or interesting depending on our end goal. So you get, if you want to live in the small mass, very short regime, you could be a kind of the side-winding snake. If you live in the very tall, heavy part of morphology space, you learn this kind of delicately balanced hopping motion. A very, very difficult part of the space to live in is to be very, very tall and very, very low mass. And here you find this very delicate but interesting solution where it's moving very slowly but methodically. And this is a very interesting solution that we ordinarily wouldn't otherwise see. So with that, this ends my part of the quality diversity section. I'm going to hand it over to Jeff.
As Joel's been talking about, and I think this is kind of a theme that we've been noticing in machine learning, is that machine learning algorithms tend not to produce a lot of diversity. So you launch one run of, say, deep reinforcement learning, and you don't get a lot of diverse solutions. You might say, well, I see things like this, where I see like 4 different styles and a lot of blog posts and tweets and things like that. And the way that this diversity is coming about is that we're doing different entire runs of the algorithm with different initial random initializations, and then we're just hoping we get this diversity, which is not a very principled way if you want to like generate a massive amount of diversity. You just keep doing inefficient runs over and over again. Now, you might think that population-based methods in general would give you that diversity. That should be the raison d'etre. But actually, it's not true. So here's a video that my colleagues and I produced a few years back
we gave an optimization algorithm these 4 building blocks for a soft robotics problem. The goal was to have the robot move as fast as possible. And then we produced this really nice video where you see this parade of like very different quirky solutions that are also kind of fun and high quality in different ways. But again, we use the same trick that you see from DeepRL, which is that we have different entire runs, each of which produces one of these. But within this population, they're all pretty much converged on one of these solutions. So what we want instead are what Joel was mentioning, which are these quality diversity algorithms, which you run them and they go out and they find the entire set of diverse, high-performing ways to go about solving this entire class of problems. And if we could get that, then we might have, be able to do a lot of interesting things that I'm going to tell you about. So Joel already told you about the first one of those algorithms, NSLC, and I'm going to tell you about a second major family that was co-invented by my long-term friend and colleague Jean-Baptiste Marais and myself in 2015. And this is called Map Elites. And here's the algorithm. It's, the acronym is a bit of a mouthful. It stands for the Multi-Dimensional Archive of Phenotypic Elites. But it's quite simple. What you do is you start off by picking dimensions of variation that you care about. Later I'll show you that you can learn these automatically as well. For example, if you wanted to search in the space of robots, you might want robots with different heights and weights. And then all you do is you discretize that space and you say, we're going to look for the highest performing thing on every one of those cells. So the way that you can do that is you can start with a random organism, you can evaluate it, and then you can get both its performance, which in another language is fitness, and you can get its phenotypic properties of its height and weight, and you just put that creature or that solution into that area in the bin. Then you grab something out of this archive here, and you randomly perturb it, and you figure out its new phenotypic properties or its characteristics, in this case its height and its weight, and its performance, which is shown here by color, and you put it in that cell in the grid. And then you can grab another one out of the archive, you can perturb it again, and maybe if it's better than the current champion in a cell, you swap it in. And that's it. So you just constantly are looking for the best thing you've found so far in each one of these cells in this map. So what's nice about this algorithm is as opposed to doing what most optimization algorithms do, which is to return a single high-performing point, this thing should go out and it should show you the entire surface of possibilities within your space. That I can do well here, but not here, for example. That there's a peak or a mode of performance, high performance over here. That I can do well with like tall, skinny robots or tall, fat robots, but not with something that's kind of an average of the two. So we actually ran this problem on that soft robotics problem that I showed you a video of. And we tried to, the dimensions we cared about were the number of voxels total in the robot, so how big it is, and also the percent of this dark blue bone material, because historically it wasn't using that material. And if you look at classic optimization, which in this case is just a black box evolutionary algorithm, you can see it doesn't cover much of the space of possible types of solutions, and most of the performance is very low. If you add in diversity in the form of that multi-objective flavor, which is a kind of a combination of both diversity and performance, you can see that the performance is higher. I don't know if you can see that's yellow there, but it still has barely scratched the surface on what's possible in this space. In dramatic contrast, Map Elites does this with the exact same amount of computation. It fans out and tells you everything that's possible in this search space and illuminates the fact that you have a mode here and a mode here that you can't do very well up here. What's also interesting in this kind of algorithm is that if you look through the actual solutions, distance in the map is informative because nearby solutions are of similar type and far away solutions are of dissimilar type. So for example, if you go right here, you'll see a solution which is kind of this motif that has legs on the front and back and kind of a back in the middle. And as you sweep up the dimension of the amount of dark blue bone material, it kind of goes from a mostly non-bony back to a very, very bony shell like a tortoise. But these things all kind of look like relatives of each other. And you can go down here and see variations on a theme, or you can go up here and see variations on a theme. So these all things look related to each other because of that distance. And that's going to become important later on. We can harness that property. Another nice property of these algorithms is they tend to be lower variance. So different runs of traditional optimization, as we saw with DeepRL and population-based search, produce wildly different solutions, whereas different runs of Map Elites kind of tend to repeatedly tell you what's possible. Not exactly the same, but pretty consistently. Also of interest is not only, this is a different problem here, but it doesn't really matter. What is also interesting is not only will Map Elites fan out and give you more points and higher quality points across the map, but if you just look for the single best point returned by the algorithm, Map Elites will often give it to you. So here it's being compared against NSLC and traditional evolutionary algorithms. And Oh, sorry, I just realized you can't see my pointer. Okay. The nice thing about this is that it's producing an actual better single point, which is kind of counterintuitive, because traditional optimization's only job is to look for one high-quality point. But Map Elites is producing a better high-quality point. So why is that? Well, I think the answer gets back to this issue of avoiding local optima and avoiding deception. And one way that quality diversity algorithms do that is via what we call goal switching. So imagine if you're a scientist and you're trying to, say, get an iCub or a robot to walk. That's what you want in your head. And you start an optimization process to say move as fast as possible. And all of a sudden what you see is a crawling robot. Well, you could say that's a really bad idea, that's a dead end, I don't want to do that, and so you change your reward function to make sure that its knees aren't touching the ground. Or you could do something totally different, and you could say, I should catch chance on a wing here. That's a nice serendipitous discovery. I'm going to say, hey, this is great. I have a crawling robot that's doing pretty well. I'm going to now fork my optimization process and simultaneously try to get better and better crawling robots, and maybe continue on with my original reward function, which was some sort of walking robot. And maybe you get a robot that balances, and you say, that's great too. I'll add that as an additional objective. And what's probably going to happen that we see over and over and over again is eventually one of these strange things like crawling or balancing ends up being a really good stepping stone to ultimately getting a nice walking robot. And so you want to keep these innovations as they come. So this is all laid out really well in the book that Joel and Ken wrote, Why Greatness Cannot Be Planned. And if you look through the history of science and technological innovation, what you find is you almost never get an intuitive straight path to an ambitious goal. If you want to make microwaves, it turns out that you had to be working on radar systems, because that's where they came from. If you want to build computers, you have to be working on electricity and vacuum tubes. And if you want to produce clean energy, you don't try to make burning of coal and oil less and less polluting. Instead, you fund a physicist to think about light beams chasing them at the speed of light on a train. You get Einstein and E equals mc squared, and then you get nuclear power. So the general idea is that we want to kind of capture serendipity within our algorithms. We want our algorithms to recognize when something serendipitous and amazing has happened, and let that continue to kind of do its thing. And we get that through this notion of goal switching. So the idea is that in this map, there's each one of these cells here is kind of a different optimization problem. We want you to solve this problem in this way or that way or this other way. And if a solution in the middle of the map happens to be all of a sudden be a really good solution to a totally different problem far away in the map, we catch that by just moving that as the champion to that cell, that problem, and optimization can continue to work on that simultaneously in parallel. So if you look at the end of a Map Elites run, the final champions, we can actually then look at where did they come from, where were their parents, if you will. And if you look at this map, what you'll see is that the arrow tells you that the tip of the arrow is the final solution, and the beginning of the arrow is where it came from. And sometimes it's very nearby, and sometimes it comes from within the cell, but sometimes you make these really, really big leaps. So you needed to be working on this totally different problem in order to kind of lateral over and eventually solve this other problem. Here is a full lineage. You take a final champion and you trace it all the way back through time to all of the different cells that its ancestor visited, and what you see are these wildly circuitous paths through the space of possible solutions. You would never probably have picked this as the curriculum by which to get to an actual final point, but this algorithm can do that on its own automatically. So what's really great in these algorithms is they're simultaneously pursuing many overlapping curricula. They're kind of bet hedging. Maybe you should go study algebra and then Calc 3 and then linear algebra, and then you'll become a great machine learning researcher. And now you should study philosophy and humanities, and then you should study Calc 3, et cetera. And it's kind of trying all these things, and then finally you get Jeff Hinton and you declare victory, and in hindsight you go back and trace the way to get there. So another algorithm in which we study these properties is called innovation engines. And this starts from the assumption that both natural evolution and cultural evolution and quality diversity algorithms are all innovation engines because they share this very, very simple recipe, which is that you start with a set of things and then you generate permutations on those things. And if those things are interesting and or high performing, you keep them and you add them to your set. And you expand in this ever-growing set of stepping stones that can lead you ultimately to really interesting things. So we wanted to try to create one of these innovation engines, and the way that we did it is that we decided, well, so far all of the QD algorithms that had come before this work all had a very simple notion of what constituted being interesting or high performing. Maybe a robot that moves fast, or something very easy to measure. In this case, we wanted to say, can we have a measure of interestingness that is more kind of abstract and hard to quantify? So we wanted to use deep neural networks. And we said we're going to try to generate images. This was like before the GAN craze had really taken off. And so we said we're going to use a trained deep neural net AlexNet. And we're going to try to generate an image that lights up each of the classes in AlexNet. And so each bin in MapElites is one class in AlexNet. And if you're the best image ever for that class, you're the highest confidence scoring thing for that class. According to AlexNet, we keep you, and then we'll just perturb these things. We also wanted to try this with these very tiny little networks that are an interesting encoding called CPPNs, which Ken is going to tell you about a little bit later. And there's lots of deception and local optima. So what we found in this innovation engine work is that if you just have one class, like if I pick the water tower class, and I try to optimize one of these little generator networks to just produce a really good water tower, what I do is I frequently get stuck on a local optima, which is what you see here in the top row. And it gets stuck on one design, and it can never get off that set of local optima. But if you have 1,000 objectives, which are all the classes of ImageNet, and you let things goal switch between these classes, then really interesting things can happen. For example, early in this run, it lands on this kind of dome that looks like the moon, and it gets to about 51% accuracy according to AlexNet for being a water tower. And that is stuck. We actually did a counterfactual where you just run that individual niche forever with that solution, and it never leaves that concept. But some other innovation came from a different class, which just kind of came in and took over in that niche, and that basically led to a completely different style of solution that ultimately got to 98%, and in my opinion, looks like a much better water tower. Now you can quantify these effects. So if you compare MapElites with 1,000 classes versus a whole lot of different runs with MapElites with all the different classes of ImageNet, where you average performance, you see this massive difference in the final performance of these algorithms. And as you change the number of objectives, the more objectives, the better, because the more goal switching you have, which you can see on these slides here. Now, another really nice thing about these algorithms is they have what are known as adaptive radiations. So these are really, really important things to have in our algorithm. Once you come up with a fundamental advance, whether or not it be bilateral symmetry or the notion of like a four-legged body plans or arms and legs or fingers, that central innovation can fan out and radiate out into all sorts of different niches or problem spaces. This happens both in natural biology, but it also happens in technology. Once we invented the computer, it was realized, oh, that's a really good solution to lots of different scientific and technological challenges, and that innovation fanned out. But once it fans out, it doesn't stay in the same shape. It gets customized and specialized to all of the different situations that we want to use that technology. And so you have an innovation, and then it percolates out, and things get built on top of it. And then there's an innovation over here, and that fans out. And you get these radiations through technological space. And you can see this in quality diversity algorithms. So this is one of my favorite plots of my entire scientific career. Here we have the innovation engine, and early on in the run, there was one little network that produced this dome, this red and black dome at the very top here for Abaya. And that central innovation fanned out and radiated into all these other ImageNet classes, such as volcano, mosque, water tower, beacon, yurt, church, planetarium, obelisk, and dome. So we want algorithms that come up with a good idea and then harness that good idea in many different ways and build upon it and build upon it and build upon it. Now, this idea might sound familiar. This idea of goal switching might sound familiar to you. Recently, there was work in this community, traditional machine learning, called Hindsight Experience Replay, and it's actually remarkably similar. The idea is you have a single RL agent that's goal conditioned and it's trying to get to a particular goal. And if you say, hey, go to the back of that room there, and it happens to go over there, as opposed to saying bad robot and giving it 0 reward, you say, fantastic, now I know how to get over there. And you add in a goal that says, I want to be able to get there, and I already know how to do it. And then you keep doing that until you kind of learn to go everywhere. So effectively, that is a QD algorithm. It's learning ultimately the highest quality way to get to a diverse set of goals. But in this case, it's not a population of agents. It's a population of goals kind of within the head of one policy or one agent. So that's a nice example of similar ideas working out great in deep reinforcement learning. Another insight behind QD algorithms, which I think is really interesting, is that we frequently don't want just a bunch of specialists. Maybe that's what you're thinking in the audience. It's like, this is a great way to get an entire repertoire of specialists, but often we want generalists. But you can use these ideas and algorithms also to generate generalists. So we came up with this idea called CMOA, with Joost Huizinga and myself, and where the idea is that we want robots that can perform many different actions or skills in different situations. And the insight is that if you want a robot, say, to perform these 6 tasks here, then what you can do is you can get a curriculum that's kind of slowly, first you learn this task, then you learn this task, then you learn this task. But you don't know which is the right curriculum. But if you use the principles of QD, then you can have one niche per single atom task, and then one niche per combination of tasks, and you can end up with this kind of exponential set of tasks that you're willing to simultaneously optimize for. And solutions can start by getting good at 1, and then they happen to be good at a 2, and then 3, and then maybe they go back to a 2, and you can trace all sorts of wild and crazy curricula through this set of possibilities, and ultimately you might get to a solution to all of the tasks. And when we quantify this, this strategy works quite well. So here's a quick video, for example, of a robot that learns how to turn left, turn right, even do a karate kick at the end, and the other tasks as well. So I want to quickly try to tell you about some of the other applications, because one of the things that we found with QD algorithms is that there's so many good kind of basic ideas and healthy optimization going on that once you have this set of high-quality, diverse solutions to a problem, there's really a lot of things that you can do with that you might not normally be able to do with traditional machine learning algorithms. So we had this paper that was on the cover of Nature in 2015 on robots that can adapt to damage and ultimately produce state-of-the-art damage recovery. So if we want robots that can get out into the world and help us put out forest fires, find survivors, just get out of the laboratory and into our homes, we're going to need to deal with the fact that robots inevitably will become damaged. Now, modern learning-based approaches, as we all know, are extremely sample inefficient. We cannot just run them live in the world. If we ever can do that, it's usually on very simple robots with low-dimensional state spaces. So what we look to is animals for inspiration. And animals, in contrast, have very, very different intuitions. They start out with intuitions for totally different ways to move. And then if they become damaged, they conduct a few intelligent tests, and then they pick a behavior that works despite injury. So we want to kind of algorithmically produce that pipeline. And the way that we do it is that we harness the ideas of QD. So here is the robot that we were using in this experiment. There we go. And what we're going to do is we're going to launch a map elites algorithm ahead of time in simulation, and its goal is to find a whole lot of different ways to walk. And so the way that we did that is we have a behavioral characterization. Remember, we have to define the dimensions of this grid. So this is a 6-dimensional hypercube. Each dimension is the percent of time that a given leg is touching the ground. So you have to learn without, learn without ever using this leg, and then learn how to walk without ever using this leg. Learn how to walk with using this leg 10% of the time, 20% of the time, all possible combinations. The original search space here has more molecules than there are in the solar system. The final map produced by Map Elites are 13,000 high-performing gates. Here's an example of one of the gates, and what you can see is that it walks. Oh, that's not working. You gonna work for me? No. All right, well, this gate uses that leg 10% of the time, and then another leg another 10% of the time. There was also, are these all my videos dead? That's a shame. Will it work here? Yes. All right, well, there with the humor. But the idea here is that there was a gate. We challenged optimization to try to produce, what? Oh, that's not even working. Okay, never mind. I'll just skip that. Okay. I don't know if the AV people can help us get the videos working. I don't know what's going on there. So one thing I want to point out is that this map elites algorithm has figured out 13,000 different ways to walk. And now, at game time, the robot has become damaged and we need to figure out what to do. You could say that I should try the top n gates in this repertoire. But remember, nearby gates in this map are similar, so that would be a pretty bad idea. Instead, what we want to do is kind of try one gate. If that family of gates doesn't work, rule that out. Try a different gate. If that family of gates doesn't work, rule that out, and keep going. And so we can do that by combining map elites with Bayesian optimization. So the general flow here is that the prior of how well each gate works comes from map elites. The posterior gets updated as we do experiments in the real world with Bayesian optimization, and Bayesian optimization will update the posterior estimate of how well each of these gates work, and then we can just stop once we have a high-performing and enough robot. So here's kind of a one-dimensional example of how this works. We run map elites ahead of time to kind of figure out how well we can do at each point along this behavioral characterization. Then we try our highest performing thing. If it doesn't work, we update our prediction for how well that robot does. And then here's where the magic happens. You can also update the prediction for nearby points as a function of distance, both the mean and the uncertainty, because that experiment taught us a lot about the robot near, all the robots in the area near where we tested, and didn't teach us almost anything about robots that are far away. And that allows us to run this. Then we can just stop when we have something that's good enough. Now, will the videos work? Oh, here we go, good. All right, so here is the original robot. It's moving at 0.25 meters per second. Then it becomes damaged, and that original gate no longer works. It's down to 0.03 meters per second, and so we have to adapt. So we launched this process, and you can see the prior, in the map here, the colors are the original coming out of map elites from simulation on an undamaged robot predictions, and then we'll test one of them, and you'll see we'll update our posterior prediction of these performances based on what happens in the real world. When we find out, for example, this gate here doesn't work very well, and so you'll see kind of the blue color percolate through the map. Now we're on, I think, our second experiment, or third here. We're at 0.17 meters per second, or 0.13 meters per second. We then try another one, which is 0.2 meters per second, and is almost straight. And then now, in 26 seconds of real watch time, we now have the gate that has recovered the original performance of the robot, more or less, 0.24 meters per second, and walks straight, which is quite remarkable. So in about 5 experiments in 30 seconds, we have a solution. We tried this in a variety of different damage conditions. It works quite well. One of the things that we did is we compared this to the stuff that is being presented here at ICML more traditionally. So if you run Bayesian optimization or policy gradients in the original search space, what you get are these 2 curves on the bottom here that don't work very well. Everything else that piggybacked on the back of map elites are all the algorithms at the top, which really work quite well. So that was kind of the principal component of success here. We tried it on a different robot. It also works to adapt to different environments, et cetera. So it's a way to get very sample efficient learning. So I also want to point out that that work didn't actually have DeepRL in it, but there's no reason you couldn't use DeepRL. There's another team that just took our exact algorithm and dropped DeepRL in, where you use DeepRL to learn a variety of different gates, and it works exactly the same and as well. So the conclusion of that mini paper on the robotic damage recovery is that you can get state-of-the-art damage recovery by combining the kind of the creativity of QD algorithms to go out and get you a set of really high-performing, diverse things, and then you can use Bayesian optimization to sift through them and find the one that you need that works for the situation, which shows a benefit of QD and using it in kind of a new context. Now, another interesting point about all of this QD work, which you might find objectionable, is that we've been hand deciding what these behavioral characterizations are, what the dimensions of these maps are. But you can also learn them. So there's a brand new paper that did an idea that we wanted to do from the original inception of map elites, which is that you can generate some random policies, then you can do dimensionality reduction, like auto-encoding, that gives you a low-dimensional latent code that kind of captures some of the variation of your policy space, discretize that code, then run map elites within that code to find everything that's possible, and then just you can keep repeating this process over and over again to expand outwards in high-dimensional spaces and find all the interesting set of things that's out there. So that works remarkably well, which is great because that helps us expand on into domains where we have no idea what even counts as interesting. So I want to talk about another application which recently came out called this Go Explore algorithm, which is yet another case where we harness the idea of QD but in a totally different way to solve a previously unsolvable problem. So a grand challenge in deep reinforcement learning is exploration, and many of you probably know that there have been these Montezuma's revenge has kind of been like the challenge in terms of trying to solve sparse reward problems where you very infrequently get a reward. Pitfall is an example that's even harder because it's actually deceptive, because most of the time you do worse, and so the agents learn to just stand still. So what we did was we wanted to take advantage of some of these QD ideas in this algorithm called Go Explore, and it splits learning into 2 phases. The first phase is just try to explore until you know how to solve the problem. Including finding just like an open loop sequence that can solve the problem. And then in a second phase, you'll take that demonstration of how to solve the problem and you'll use imitation learning to robustify that into a neural network that can deal with stochasticity. And what I want to focus on is the first phase, because that's where we harness quality diversity algorithms. So here's what that algorithm looks like. You start in A here, which is you start by taking some random actions, and every place that you end up, every state you end up in, you add that to your archive. And then what you do is you pull a state out of the archive, you go back to it, with no exploration added, and then you explore from it. And if you get to any new states in the archive, then you add them to your archive. And then here's where the quality comes in step D. If you happen to get back to a place you've already been, but you get there in a better way, either through a shorter, more efficient trajectory, or through a higher performing trajectory, you swap in that method of getting there as your preferred way to get to that cell. So if you think about it, this is an enhanced version of Map-Elites, because I learned the fastest or the highest rewarding way to get to this point, and that point, and this point, and that point. And I have this set of policies, which is the best way to get to all of these different places. And ultimately, I'll have the best way to solve the entire game. And to skip over a lot of detail, if you look at the previous performance on this task, it's usually around 0 to a state-of-the-art of around 11,000 before this work. And the best policy using these ideas gets to a score of about 18 million and scores 1,100 levels of this game. It even beats the human world record on this game of 1.2 million. So it's really just a step change at what optimization can do when you kind of embrace the idea of an expanding repertoire of high-quality policies. On Pitfall, the story is similar. There had been no prior score greater than 0 on this task, and Go Explore basically goes out and gets a max score of 107,000 and an average score of 60,000, which is just a dramatic step forward in our ability to solve these hard exploration problems. So I think that this shows the value of quality diversity algorithms, of collecting a diverse repertoire of high quality things, and helped us solve this problem. So so I want to just briefly stop and talk about looking forward a little bit. In future work here, you can kind of think about how could we exploit what's in this map. We've shown you in the Nature paper on robotics, and you showed you in Go Explore 2 different ways to kind of harness what's in there. But I want to challenge everyone in this room who's listening to this tutorial to think about what could you do in your problem space and with your techniques to take advantage if I gave you a set of 1,000 or 10,000 or 50,000 totally different ways to solve the problem, each of which is pretty good in its own way. So one thing you could do is you could use that data to learn really good representations of the world and how to solve the problems in that world, like value functions, which could aid you with further exploration. You could also learn models of the world, because you know how to fan out and explore all these different niches of the worlds and different dynamics and ways to behave. For example, if you only optimized for running robots, you might never learn about the physics of flying. But if you had an algorithm that produced flying robots and running robots, now you can model the physics of flying creatures and running creatures and maybe swimming creatures. You might also be able to learn a lot of really important options in like a hierarchical RL fashion. I can get from here to here and here to here and here to here. Well, those could be little atoms that some top-level controller is kind of using to move around the world. You could also learn agent models, because you've fanned out and you've interacted with all sorts of different agents that if you were only focused on optimization, maybe you'd never go play with the worms in the back corner of this closet or something. But now that you do, maybe you can model how those agents behave, and maybe that's useful for some reason. So I don't know the full set here. I mean, I would like to see what this community does when they're challenged to think about all of this. So to conclude here on quality diversity algorithms, we are going to, what we think is really, really promising about this family of optimization algorithms is that you can generate this set of diverse, high-quality solutions, which is just really intrinsically interesting to understand what's out there. It gives you a bunch of options and trade-offs. Maybe the top-performing thing isn't what you want once you see that there's some other trade-off you hadn't considered. And we think, most importantly, that these algorithms have a lot of healthy internal dynamics in terms of what's going on. So they collect this increasing set of stepping stones that they can be used as branching off points. They have goal switching, so they catch chance on a wing and serendipity. They use that to avoid local optima, and as has been said, chance favors the prepared mind. So we want our algorithms to embody that concept. They also build on innovations via these adaptive radiations, where you get a central innovation, and then everything can radiate out into all the places where it's helpful and serve as a foundation for future innovation. They learn multiple overlapping curricula and bet hedging, and ultimately one will work, but ahead of time you wouldn't know which one that is if you don't kind of simultaneously push on all of them. And often, as we've shown over and over and over again, even if you are just trying to solve one ambitious challenge, these can be the best way to get there because of all of these healthy dynamics that fan out and don't get trapped by deception and sparsity in the search algorithm. So with that, I'm going to flip it over to Joel, who's going to quickly tell you about some other QD ideas in the machine learning community, and then we're going to have our Q&A. So while Joel is talking, if you have questions for us, please come to the microphone. We're going to keep it to about 5 minutes, and then we'll press on to the other subjects. Thank you.
Thanks, Jeff. So at the end of this focus on quality diversity, we'd like to draw attention to a really interesting vein of work coming out of DeepMind on population-based training, and some connections between that algorithm and as used in their AlphaStar agent to these ideas, inspired by a short paper by Arul Kumaran. So if you're not familiar with the idea of population-based training, it's a really cool idea and recommend that you read the paper. It's motivated by the idea that hyperparameters are really important to getting machine learning algorithms to work, and that efficient optimization of hyperparameters is a really important thing to make our algorithms computationally efficient. So one approach you might use is to sequentially try different sets of hyperparameters, like using Bayesian optimization, where you train one set of hyperparameters and see how it does, and use that to inform the next sample. You might do something a little more scalable and do something like random search, where you try lots of different hyperparameters in parallel. And the idea in population-based training is that you do something like random search for hyperparameters, and as you're training your algorithms with these initially random set of hyperparameters, you pause training at some point. And when you pause training, you look at which set of hyperparameters are performing better. You do sort of a greedy sort of online evolutionary search where you overwrite the poor performing sets of hyperparameters with modifications of the high performing set. And in this way, you can kind of get an adaptive schedule of hyperparameters that ultimately leads to really nice improvements in a computationally efficient way in hyperparameter search. And this has been an idea that's had lots of interesting applications so far. It helps to stabilize GAN training, which is notoriously a little bit difficult. It's been used in the recent Science paper on capture the flag. And very recently, I think just maybe a couple weeks ago, there was work out of Berkeley on using population-based training to make for more efficient discovery of data augmentation policies. But I want to focus right now on thinking about AlphaStar. So if you're not familiar with AlphaStar, it's the human performance matching StarCraft 2 agent, and uses a lot of interesting deep learning technologies. And one of the ingredients in this system is population-based training. And so in a game like StarCraft, when there's many different strategies, you might want to maintain a diversity of strategies so that you're not overfitting to whatever is currently present, just one sort of strategy that can be easily defeated by other ones. And so what they do is they have a ongoing league of agents that are competing with each other. And the idea is that by having a league and by incentivizing certain agents to perform differently, maybe one agent has a learning objective to kind of beat another particular agent, or to beat a distribution of agents, or to use more of the particular units in StarCraft than other agents. The idea is to kind of maintain diversity explicitly in this population to make overall the emergence of a really robust solution more possible. And so we're still waiting on the actual paper, but it sounds like from the blog post that there's a lot of interesting, maybe potential innovations in QD that are being introduced by this. And yeah, I think we're excited for other sorts of interesting riffs on population-based training and how it could kind of push the field forward. So with that, if you want to start thinking about the question and answer and reaching towards the microphones, we'll start our question and answer session now.
And just to be clear, this is the first Q&A. It's going to be very fast, and then we're going to get on with 2 other really cool topics from Ken, and then we're going to have a second Q&A, which is hopefully even longer and can bleed into the break if people are interested. Tag in.
Hi, thanks for... Is this on? Okay, great. Thanks for a great talk, both of you. This is a more general and sort of naive question about evolutionary algorithms. You're talking about spanning out diversity in kind of a space of policies or maybe value functions. And I was wondering what the evolutionary algorithm or genetic algorithm community thinks of as generalization, or as the class of problems you're sort of training on and the class that you want to generalize to. If there's that notion, like if it's across policies or across reward functions, how that could translate to supervised or unsupervised machine learning.
Yeah, I think it depends on which subset of the community and what they're trying to achieve. I think in a lot of the stuff that we've been talking about, we follow more of the RL philosophy, which is that you kind of are just trying to get an agent that can actually do this thing or solve this problem, and we don't usually then switch to something else. So in that sense, I guess we're guilty of training on our test set. There has been work, including by the work of the CMOA algorithm that I presented there, where we did actually train on a set, for example, of mazes, and then we wanted to generalize to different mazes. And we're preoccupied with generalization. And then obviously the Nature paper, the intelligent trial and error, in some sense is the granddad of generalization, because you're going from simulation to trying to generalize to the real world in some cases. So I think you'll see all of the above under the tent, that depending on what people are working on, they either do or completely ignore the issue of generalization. Yeah, David.
Hi. Good. Yeah, so this might be a little bit long-winded. I apologize in advance. So creationists have this critique of like the evolution of the eyeball, where they say an eye is totally useless until you have the whole eye there, and then people respond, oh no, it's nice to have this light-sensitive spot, and so on. But there's this underlying question of like, can you basically just advance via some sort of local search towards your goal? And it seems like a lot of what you guys have been talking about is sort of saying, no, that's not the best way to achieve your goal. And that reminds me of group selection, which, as I understand, is a very controversial and sort of dirty word in evolution, and is not considered biologically plausible, probably by most people, although I think like E.O. Wilson recently changed his mind about that. So basically, I'm curious, what you think about the biological plausibility about these sort of techniques that are explicitly selecting for diversity as opposed to just fitness, and if you think there's like implications for our understanding of evolution and evolutionary biology.
Go for it.
Yes, it's a really interesting question, and obviously when you have biologically inspired algorithms, there's some hope that it would connect either to help test hypotheses in biology or to maybe replicate some of the results in biology. So on group selection, I guess I personally don't have like a strong opinion on that. I think it's an interesting concept, and maybe it could be useful for some algorithms. So I guess, what was the second part of the question? Yeah.
I'll jump in on the second part, which is the style of things that we're talking about here biologically plausible? And I think that they are. And I think that one of the really interesting things is that most people think of evolution as kind of competition. That to get a better cheetah, you have to be faster than the other cheetah, and you get this race to faster and faster cheetahs. But one of the really interesting things that happen in nature with these algorithms they're trying to capture is that they're divergent, because you can win the race by being a faster cheetah, but you can also win the race by swimming to an island where there are no other cats, and all of a sudden there's no competition at all, and you've avoided competition, and that allows you to radiate out and specialize and have an opportunity to kind of maybe figure out a totally different solution to a problem that has nothing to do with being a faster cheetah. And so what you see in nature is the creation of niches on the backs of niches on the backs of niches, that once you have, for example, tall leaves, you can solve that niche by being a giraffe or by being a caterpillar. And it's not all about optimization to get better and better and better, but actually that there are all sorts of opportunities to avoid competition and come up with a wildly different solution. And I would speculate, and this is maybe totally controversial, and I shouldn't be speculating live in front of all these people, but if you had just set up the reward function to be distance, focusing on reading letters far away, like human vision, and that's all you hammered on, you wouldn't have gotten it. Without the diversion, tons and tons of niches, sometimes that benefited from a light spot or detecting a shadow swimming over me, and all these different optimization problems, we wouldn't have gotten the frequent convergent evolution of vision, which was a really complicated thing, because there would have been a deception and local optima, we would have gotten stuck on them. It's because of this divergence that we got convergent evolution of eyes over and over and over again. We have one more minute, unfortunately, so let's take one more question, and then we'll hold the rest of the questions for the second Q&A, if you don't mind. And you've been waiting patiently over there.
Testing. All right. You kind of spoke about this just right now, but when you were explaining in your talk, you were talking about multiple objective problems. What does this look like for a many objective problem? And then following that, does that even matter when you're talking about novelty?
So I think all of these ideas apply even better with many objective problems. So one of the things that I wanted to kind of convey in that innovation engine plot is the more problems that you add to these things, putting aside compute, which is a legitimate concern that we want to talk about, but putting aside compute, the more the merrier, because you have more curricula, you have more opportunities for goal switching, you have more opportunities to kind of go around local optima and then come back and solve a problem. And these things ultimately, you know, if you had enough compute, you could put in 1 million different objectives and you get 1 million wildly different solutions. But it's not like doing 1 million separate optimizations. If you're sharing compute, you have like innovations that kind of get built upon and built upon. So to some extent, it's like a complexity ratchet, if you will, where you get more and more complex and more and better things kind of over time fanning out through the space of, you know, potentially an infinite number of objectives if we didn't have to worry about compute. So I think there's a lot of healthy, this is probably, in my opinion, the best way. Most of the multi-objective algorithms don't scale very well to many objectives, but these things scale beautifully. You just pour in more compute and you get more performance. Okay, with that, we're going to, please save your questions. I know there are a lot, and we're sorry to cut them off, but we'll have plenty of time afterwards for more. We're now going to hear from Ken Stanley on a variety of fascinating subjects, including, first up, I believe, open-endedness.
Yes. Okay, and I think that a tutorial on population-based search would not be complete without some discussion of the challenge of open-endedness, and I call it the grand challenge of open-endedness. And I'm glad to have this opportunity to talk about this grand challenge because a lot of people don't really know about it, but it's really a fundamental and exciting opportunity, and I hope I can encourage some people to think about it who weren't aware of the challenge that I'm about to describe. So we've been talking about divergent search, really. I mean, we're more familiar with thinking convergently, but we've been talking about these divergent algorithms that try to find many interesting points in a space and sort of show what's possible, or at least of any interest. But if you think about it, in any given domain, if we choose a domain like, say, robots that we want to be able to walk in different ways, what is possible is, at least of any interest to us, is finite if we choose any given domain. The amount of quadrupedal gaits that we can find that are of any interest. And so it is interesting to think about whether there are algorithms that don't just find what's possible, but also invent endless new possibilities. In other words, if we found all the possible ways that a quadruped can walk, then let's move past quadrupeds and find a new problem and use the skills that we've gained to solve new problems and forever. And this is open-endedness, and I'm going to sort of illustrate it in some more depth. So QD, which we've been talking about, seems to get close to this issue, but it's not quite there. Because this is not how to learn something. Like, this is usually what we do in machine learning is we say we have problems, we're going to try to learn solutions to these problems. But really this is like, is there such a thing as an algorithm that will learn everything? And so, like, we can think about something like a human learning to play a video game. I mean, that's inspired a lot of reinforcement learning. We've seen algorithms learn to play video games, and that's interesting. But the history of all of human invention is beyond just interesting. And the history of human invention is something that humans did. And so there are algorithmic principles behind that kind of a process, or something like natural evolution, which is the ongoing creation of all the diversity of life on Earth, which we've alluded to before in this talk. And so, like, this tree of life is interesting in some sense because it's only one run of something. It's not like there was a separate run for every creature, and we found all these creatures through different optimizations. Rather, this isn't actually optimization. This is something else. This is open-endedness. In a single run going more than 1 billion years, and it never seems to stop inventing new things. And in fact, it's interesting just to consider that this doesn't require human intelligence. Like a process like this evolutionary process, of course, there was not human intelligence behind it, and yet it's the most prolifically creative process that probably we've ever seen. And yet, somewhere inside of that, there's human-level intelligence, like this tiny moment in this endless saga, and yet it is created by something that itself does not require a human level. And so basically what a process like this is basically a process of endless surprises. Like, you can't predict at the outset or at any given point where it might go in the future. And it just keeps going, and look at the things that it creates. Like, these are really, really remarkable and amazing discoveries beyond our capabilities in engineering today, like photosynthesis, or flight, the flight of birds, or human-level intelligence in the brain, all in one single run. Very different, divergent types of discoveries, but all in the same optimization process. Now, something like QD seems to move in a direction like this, right? Because it's saying that, like, we're going to be fanning out into the space of what's possible and trying to collect the highest quality we can all across that space. But this isn't really like QD if you think about it, because QD doesn't invent new problems. Like we may solve the problem of ambulation on land, but that doesn't mean anything about flight, and we never would go there. And there's some other ideas that are floating around that actually are related to open-endedness, but none of them are quite there. Like for instance, a GAN does seem to generate new stuff, right? I mean, it can generate images you've never seen before, for example. But if you think about it, if you exposed a GAN to billions of flatworms, and flatworms are actually our ancestors, so we evolved from flatworms, you'll never see a human come out of it. Because what a GAN does is interpolates among the points that it's already seen. It will not extrapolate billions of years into the future to something truly new and novel. And so there's something beyond this kind of generativity that we're talking about when we're talking about open-endedness. There are also ideas like self-play, which is also related to something called coevolution, which I'll talk about a bit more, both of them, which also touch sort of on the road towards this open-endedness concept, which is that, like, if you have a competition where things are playing against each other, you get this kind of arms race dynamic where there's a ratcheting effect. And maybe there's something in there where you get a diversity of strategies that then fan out into the space of what's possible. But the thing is, even there, like, if you have something like AlphaGo and it's playing Go, well, it's only going to improve at Go, right? Like, you're never going to invent a new game and then come up with something else. And so there will never be a new game in town. So what kind of algorithm is open-endedness? And one characterization that I like for this is sort of like it's the never-ending algorithm. An algorithm that you would never want to stop and that you'd be willing to come back a billion years from now and see what's happening because it would still be interesting. And it's interesting to consider that there is nothing like that right now. I don't think there's a single algorithm someone can point to right now where it would be worth coming back in a billion years if we could run it for that long. And Earth is kind of this never-ending algorithm. And so that's sometimes referred to as open-ended evolution, but I think we should more generally talk about open-endedness, because this isn't just about evolution, although we used it as a motivator. This is about all kinds of processes that have this property. Like, open-endedness refers to, like, the history of all of human innovation, all of the inventions that we've ever created in a single process. It's not an optimization process where there's one uber invention that we're trying to aim towards and everything else is just a stepping stone to that. Rather, we're just fanning out and diverging and building on each other's discoveries with no end in mind. Or the history of art, or science, or architecture, etc. Like, all of these things that have these kinds of diversity of divergent outputs are open-ended processes that don't end and just keep on building and extrapolating from where they've been. And so, you know, why don't we create these kinds of algorithms? Why do we only try to solve problems? Why don't we create something that can do this? And so, actually, there is this one community which is a very sort of small niche community, which many have probably not heard of, which has been studying at least the open-ended evolution aspect, and it's called OEE. And there you can see like a graphic from one of their meetings there. And so it's very small and it's not mainstream, and most people don't know about it. And it's a shame that this is true, I think, because if you think about what open-ended evolution is, this is actually the power of creation, literally. We're talking about like a process that created all of living nature. And this could be potentially transformative if we could harness processes like this or create algorithms like this that you would never want to turn off, because you'd have boundless creativity on demand. Discoveries beyond the scope of optimization. Because as we've seen through QD and so forth, there are deceptive problems, like especially the extremely ambitious things like human-level intelligence, where probably the stepping stones you need to traverse to lead to them don't look like they actually would be the things you'd want to optimize to get there. And so open-endedness is the kind of thing that traverses those stepping stones. So I would say that, like, to create a process like this is a huge challenge algorithmically, and it's a grand challenge that is on the scale of AI. In fact, it may be the path to AI itself, because the only example we have of creating intelligence at our level is an open-ended process. So why does it get so little attention then, this concept of open-endedness? Well, actually, one problem, like, for this field, to the extent that it's been studied so far, is that a lot of what we've seen so far in direct research on the open-ended processes, and it has been in what have been called like A-life worlds or artificial life worlds, which are like these little ecological simulations. And the problem is that when people see this, they usually think of this as sort of like a completely different problem than something that we would be interested in machine learning. They're like little simulators. Maybe somebody's using a little toy to learn something about biology, maybe something about ecology. But it's unfortunate because actually these are about something bigger, which is to truly understand what actually bootstraps you into a process that just explodes in complexity forever. And if you think about it like that, then this is actually like a really deep and interesting problem. And it's kind of unfortunate that we have sort of not appreciated what the deeper fundamental insight is that we're seeking behind these kinds of things, because I think there could have been a larger community involved in thinking about how to create something like this. And so really the point is, it doesn't have to be a world. I mean, you look at these worlds and you say, it's not the kind of work that I do. I don't do that kind of work, like a little creatures running around eating each other and eating food and things like that. But it doesn't have to be a world. A world is just a conduit to understanding. It doesn't even have to be a metaphor for organisms on Earth. You know, deep learning can and should play a role here, because we can also imagine gradient-based processes being open-ended with no problem at all. That makes total sense. In fact, people are open-ended. Our lifetimes are open-ended. Many of us invent many things in a divergent process throughout our lifetime. And collectively, we as a society and a culture are behaving open-endedly. So what we're seeking then is the fundamental conditions for a divergent and creative process that would never end. And that could be applied to anything. So not just some kind of ecological world simulation. Like, think about like the designs of things like buildings, vehicles, furniture, clothing, equipment, etc. Endless designs, repertoires for controllers like vehicles and robots, and etc. Generators of things like art and music, which obviously follow open-ended processes, the history of both of those fields. Imagine worlds that you could create that unfold open-endedly, so they would have all the granularity and originality of ecologies on Earth. I mean, these would be amazing places to explore because they're actually just as open-ended as nature. We would have a renewed understanding and acceleration of the process of human invention, because if we could actually formalize algorithmically how processes that are open-ended actually work, then we would understand ourselves better as well, and how to actually implement those processes culturally in a more effective way. You can imagine human-coupled open-ended systems. So of course, ultimately, we're interested in open-endedness that will produce things that interest us, and those kinds of systems then would have maybe us in the loop. And even maybe intelligence itself could be one of the outcomes of open-endedness. We can actually discover perhaps intelligence through an open-ended process, or maybe we need to have an open-ended process to do that. So, like I said, we talked about QD, and QD is a step in this direction because of its divergence, but QD algorithms won't invent forever, because we have to ask what would happen when the space of the possible is filled, and there's only so much of a space there in any QD algorithm. What causes new possibilities to arise and forever? What would allow that to happen virtually forever? And the answer is that a system that's truly open-ended, it needs to generate new opportunities and search through them at the same time. In other words, there's a missing element here, which is the new opportunities. We need new things to do to continually have the ability to find new solutions to problems. And so that's why Earth is open-ended in all of its contexts, from human culture to evolution, is because opportunities are being generated to do something new at the same time as solutions are being searched through those opportunity spaces. And so, as an example, because trees evolved, there was an opportunity to be giraffes. And if there hadn't been trees, then there wouldn't be an opportunity for giraffes. And so the things that are evolving are creating opportunities for new things to evolve, and this is a continual process, and this is a missing element currently in non-open-ended types of algorithmic processes. So how will we achieve open-endedness then in algorithms? And of course, this is a great puzzle, but great puzzles can lead to surprises. And so we can expect some counterintuitive type of insights along this path. And I wanted to show you one example of something that provides some clues, because this is actually really fun to look at. There's very few systems, I think, that exist, artificial systems, that exhibit properties of open-endedness, but this is one that does, and it's called Picbreeder. And it is really interesting because it is an artifact which has open-endedness inside of it, and we can actually go back and look at the history and see what happened. But there's a big caveat that I want to admit and concede about it, which is that there's a human in the loop, which is basically cheating. Because really, what we're doing is we're riding on the backs of the fact that humans ourselves are open-ended. I mean, we have the capacity of open-endedness already in our intelligence and in our culture. And so, of course, we're piggybacking on that here. And that's important to recognize, which means you don't fully understand how to implement an autonomous version of such an algorithm. However, it's still very instructive and interesting to see it anyway, because we rarely see artificial open-ended processes. So let's take a look at this just for a moment and see the kind of thing that it does. So the main idea here is that we're going to create a system where you just breed pictures, but the point is going to be that anyone can follow up from anyone else's discoveries. So there's no unified goal for the system. So what do I mean by breed pictures? I mean, here, each of these 15 images is generated by a kind of a neural network, which is just randomized at the start. So we have 15 randomized neural network images. This is not a GAN. This is just a single neural network that outputs a single image in all cases. So these are unrelated to each other. They're just different networks that are random. I pick one, and I say, OK, let's just generate some perturbations of the weights of that particular image. And then we get some perturbations, and I can pick another, and we get some perturbations, and so forth. And so the question is, if we implement this process in an online, in an internet-based service, so that people can go on the web and do this collectively, and if I discover something, I can publish it, and you can branch from it and evolve it more. It's very simple. What kind of things do you think you can find? And I mean, look at the space for a second, because it's not too interesting if you look at it like this, but it gets really interesting if you see what happens when you put all these people into this world without any final goal, and you get this. And so this is actually, I think this is kind of hard to believe when you first see it, that you see these kinds of images, because it's coming from like these really modest beginnings. And this is really different from the kind of stuff we're generally seeing in deep learning, for example, because you have to remember, these are the outcomes of dozens, or maybe at the most, hundreds of iterations. Right? We're used to enormous amounts of search, thousands or millions of iterations of search. These are extremely small peanuts numbers of iterations, and yet finding these images. This is not an output of a GAN. This is like perturbing something 47 times, and you get something like this, something random. And so how is this happening? Well, the explanation is that this is what happens when you have genuine open-ended search. The opportunities that the search is moving through are basically the brains of the individuals who are playing the game. And so different people like different things, and different people branch off from different points depending on what their personal preferences are. And so what you get is what looks like this, which is what a biologist might call a phylogeny. And what you're looking at here is you're looking at like each one of these connections here is a point where one person branched from another's discovery. And so people are branching off of each other's discoveries in a divergent way. And you're getting this expanding divergent phylogeny. And that's what explains why you're getting this kind of a gallery at the end. And of course, these are just a small sampling of thousands of images that have been discovered. And so what can we learn looking at what happened in a system like this, because there's so few artificial systems like this. And here's something that we discovered, which I think is an important insight, a fundamental insight about open-endedness in general, which is that in this system, people only found things that they were not seeking. And if you just try to process that for a second, it's really counterintuitive and kind of astonishing. Like if you look at a system like this and you're used to thinking about something like gradient descent, well, you might think about, well, of course, we're going to descend into the images that are the optima that we're seeking. But this is not the case at all in this system. People only found things they were not looking for. And how do I know something like that? Well, I know that because I know everything, and we know everything, about every single step that was ever taken in the history of this entire system, so we can look back and see. And what we see is, when we look at the stepping stones, which means that somebody discovered, for example, this, which looks like an egg with a hat. That's what I call it, an egg with a hat. This egg with a hat was branched by someone else to get to what looks like a teapot. And the point here is, it's inconceivable that the person who discovered the egg with a hat could possibly have been thinking, just what I need to get a teapot. That's inconceivable. Or it couldn't possibly be the case that the person who branched in and got to the teapot was thinking, finally I needed an egg with a hat. Or I needed this dish to get to a skull. Or I needed, it looks like a letter G, to get to Jupiter. In every single case, the stepping stone that was necessary to get there could not possibly have been discovered with the final discovery in mind. And try to just digest that, because it's both fascinating and concerning in some way, because we run a lot of our algorithms with the complete opposite spirit, that we're trying to find something, and that's the way to guide things to get there. But this is the opposite. This is you only get places because people are not looking for those particular solutions at some certain point in time. And so it's important sort of like as an insight in terms about open-endedness as well, because it tells us something about why open-ended systems are so powerful. Because they're not looking for anything in particular. You know, the objective of evolution on Earth is not to create human brains. You can't find anything in the description of evolution that would predict that this is a process designed to produce human brains, and that is why it produced human brains, and that is why it produced flight, and that is why it produced photosynthesis, etc., is precisely because it's not trying to. And it becomes powerful because it is open to discovering everything. If you're not open to discovering everything, then you're going to discover nothing because you'll be deceived. And this is why we're seeing this bizarre principle emerge in this complex space, is because if you look at the stepping stones that lead to any particular discovery, like the skull in this example, you will find that if you were looking for that, you wouldn't traverse these stepping stones because they're deceptive. It doesn't look like you're moving to skulls if you find a donut. So you have to be willing to be interested in donuts and not skulls in order to get to skulls. And this actually was one of the inspirations for novelty search. Okay, but then okay, that's really interesting, but I remind you that there were humans involved there, and that's cheating, right? So it'd be interesting to be able to create algorithms with this property without humans. And so this leads to a question that people have asked who are interested in open-endedness, which is, what are the necessary conditions then, from a formal perspective, if we wanted to write an algorithm like this that actually works this way? And people have hypothesized a whole bunch of necessary conditions for open-endedness. It goes back to Waddington, who was a biologist in 1969. Tim Taylor later proposed a bunch of conditions, and there's been other attempts to propose conditions to get to sort of more a formal algorithmic type of set of requirements for how do you actually create an algorithm that has these properties. We made our own attempt, myself and Lisa Soros, a few years ago to propose some conditions. And so the fundamental goal of this kind of a proposal is to describe a system that would generate new challenges and how to solve them. We need new things to do always, and we need to be able to solve them. We need to be able to search for new ways to solve them in the spirit of something like QD. And so this is just for a taste. I don't want to claim, and I certainly don't even believe, that this is a definitive set of conditions, because no one has yet created something that I think is satisfyingly reminiscent of nature or human innovation. But here's an attempt just to give you a taste of like what is the thinking like when we're thinking about open-endedness and algorithms without humans in the loop. First, let's say that there has to be some minimal criterion to proliferate. In other words, if we're going to move in a certain direction, which is what I mean by proliferate, we need some criterion to say, yes, we're going to continue in that direction, or else we have to shut it off, because we can't go in every direction. Second, individuals have to create novel opportunities to satisfy that minimal criterion. This is where the new problems comes from, like the trees and the giraffes. It's the individual things that we're evolving, or that we're searching for, or that we're optimizing inside of this system that need to actually create the opportunities to find even more new things. So we need to have that kind of a dynamic that's, in effect, coevolutionary or self-play-like. So third, the individuals in the system at some point need to decide for themselves with what or whom to interact. And this is because we can't project millions or billions of years into the future who might be juxtaposed with whom. Like, we can't know that the giraffes will need to interact with the trees. It's the giraffes themselves that move to the trees. And also we need the ability to increase the size of representation, because since this process is supposed to go forever, we have no way of anticipating the complexity of the final solutions that we might want, because there are no final solutions. It's just going to keep going. And so just to point out one thing here, when we talk about with what or whom to interact, well, that's certainly reminiscent of coevolution and self-play. And this is a long studied topic. And I just wanted to highlight that there's a long history of what's called coevolutionary optimization. And there's also now recently what's called self-play. And these are very tightly related, actually, say even the same field, even though they're going by different names. And like in coevolution, there were different kinds, like there was competitive, cooperative, and test-based. A lot of it draws on game theory, like there's what's called Pareto coevolution. And then recently we have things like self-play, where you have like the OpenAI DOTA results, AlphaGo, AlphaStar, StarCraft, etc. All of these kinds of results from self-play. And so these things would certainly come into our understanding of open-ended systems. But like I said, it's not sufficient to just look at those kinds of self-play scenarios, because we also have to figure out a way to create new opportunities. So if it's all inside of StarCraft, then all you'll ever have is StarCraft, right? StarCraft players that get better, hopefully, over time. But we want more than just that in an open-ended system. And so if we say we have the right conditions, and we have something coevolutionary in some sense, then we can maybe create algorithms that exhibit open-ended properties. And this was one of our first attempts to do this. This is called minimal criterion coevolution, which tried to abstract these necessary conditions outside of like the A-life worlds, and sort of say, let's make an algorithm that's totally generic. And so the idea was, we'll have a minimal criterion, we'll have self-generating opportunities, and we'll have this two-population kind of idea. Like there'll be one type of thing that's co-evolving with another, and one thing provides opportunities for the other. And so the idea here was, let's do mazes and maze solvers for a first test. So the mazes are co-evolving with the maze solvers, and the mazes can get increasingly complex, and the maze solvers, which are neural networks, have to become increasingly complex to match. And we saw in these runs that we could get increasingly complex mazes and increasingly complex solutions to those mazes. And it's interesting, at least intriguing as an initial hint at what could be accomplished if you consider that it might be the case, maybe assert that if we ran this for 1 million years or 1 billion years or say forever theoretically, these mazes could become as large as the galaxy, and the neural networks to solve them would come with them. And so there's some taste of the increasing complexity aspect of open-endedness in an algorithm like this, but it's just the beginning. And actually, we're going to see something even more recent called POET in a moment that Jeff is going to talk about, which is our most recent attempt at open-endedness. But I just want to close this section on open-endedness by just pointing out the field is just beginning. Many challenges remain. We want to be able to generate endless high-quality, diverse, and interesting artifacts, and that's obviously a huge challenge. Killer applications are critical for motivation. People want to know, why do you want to do this? I think we can see some of the inspiration inside of things like QD and some of the results that Jeff shared, but we want to be able to show that in the context of a more open-ended type of a system, why this is very important. And I think it is important because open-endedness may, like I said, be a path towards intelligence itself. The measurement of success remains controversial, so this is just an interesting problem in itself, is how do you measure the open-endedness of a system? How open-ended is it? And there's a lot of argument, like within the small community so far, about how this should be measured. This is the power of creation, so it can't be understated how significant this is. Like all of living nature is a product of a single run. To have that kind of a power algorithmically is just profound. And so when will we harness this power? I just finally want to point out that we have sort of created a non-technical intro for those who are interested in open-endedness, want to learn more about it. It's here at this link. I think these slides will become available also. So if you want to read a little bit more and get some references to follow up on. And also, Joel in my book also has a lot of talk about divergent search in general, if you want to get more in depth into some of the stuff where we couldn't get into the details. Okay, thanks. So I think Jeff is going to now follow up and show you POET.
Excellent. Thank you, Ken. And yeah, the slides will be available, and all of the papers that we've talked about today we'll put in a giant appendix at the end of citations. So if you're interested in tracking any of them down, they will be in the slides. Switching gears. So I think that you're getting the sense that we are really, really excited about open-ended algorithms and trying to create algorithms that generate their own problems and solutions to those problems, because we think that that is a key to making progress. And so what I want to show you now is kind of our latest salvo in this direction, the most recent thing that we've done to really try to push on this front. And it's definitely not the final algorithm. There's lots and lots of research to be done, but we're really, really excited about this. And so it comes from the idea that designing in reinforcement learning and machine learning in general, we know that like data is the rocket fuel of success. And if you want to achieve something really ambitious, you have to have the right data or the right training environments. So then we started asking ourselves, if that is so critical, then can we just have algorithms that generate their own data or generate their own training environments as they go? And we think that that's a fascinating question, and we think that it's actually essential to get anywhere really, really ambitious, as Ken just described. So our most recent algorithm here is this POET algorithm, which stands for the Paired Open-Ended Trailblazer. And there is a pair of things happening. There's going to be an algorithm that's generating problems or challenges or training environments, and then there's going to be a separate group of things that are being optimized to try to solve each of those challenges as they get introduced. Now, Ken just showed you the minimal criteria coevolution work, which is really cool because it was the first time that I had really realized that you could parameterize the training environment itself and just describe it, and then you could separately optimize and play in the space of what does it mean to be the right training environment. This algorithm takes it a little bit further, though, because what we wanted to add back in were some of the things that we think are really essential. One of them is that you continuously optimize within a problem. So you don't just meet the minimum bar, but you get better and better and better at it over time, because that may be a stepping stone to solving some other problem. And we also wanted to harness that idea of goal switching that I spent so much time talking about, that you want to be able to be going really well on one problem, but if you happened along the way to produce something that's really good on another type of problem, well, you should capture that and let the algorithm take advantage of that. So here's a little video that describes, hopefully this is going to play, a video that describes the algorithm. I think it does a really good job of summarizing it, so it kind of is a bit like drinking from a fire hose. But hopefully we'll just let it run. And so you see this little agent here. This is the world we're operating in. This is just the first world that we play in. But we parameterize that environment, those kind of obstacle courses, and we allow optimization to both create different environmental challenges and try to optimize a neural network with deep reinforcement learning to solve those challenges. And all of the different challenges that you're seeing here were invented by the algorithm as it's running. And also, the agent that is solving that problem was also invented at the same time. And over time, these environments get more and more complicated. Like, that's actually a really, really big gap for this agent to try to solve. And those are really big stumps for this little guy to try to crawl over. And what we find is that this system just kind of loves to innovate and push its own limits and invent new challenges that are right at the limit of what it's capable of doing, and then building off of those skills that it's learning to go and challenge and take on even harder environments like these ones here. This little creature here has little LiDAR sensors, and what you'll see is that in some of these videos, it kind of like literally runs up and then leaps over a chasm, which is quite interesting and impressive to see. These just amazing skills. Sometimes the chasms are basically right at the limit of what's even possible given its morphology. One of the things that we're interested in the future is even simultaneously optimizing the bodies of these robots, because you could imagine that maybe you need longer legs to go over them. One of the final things I'll mention here is that any of these really challenging problems, when you go back and look at it, you cannot directly optimize to solve that problem if you try to do that, either by just dropping an agent in that environment and trying to solve it because there's no curricula to get there, or by taking kind of what you would see as the direct path. Here are some solutions that traditional optimization cannot solve, but Poet does find a solution to some of these really, really crazy environments. So I will skip beyond that. So I want to quickly kind of show you how this algorithm works. So we start off with a parameter vector that describes an environment, for example, how rugged it is, how wide the gaps, how tall the stumps are. And that I'm showing here is phi1 for environment 1. And it's pretty easy because we start easy. And then what we'll do is we'll launch an optimization algorithm for theta1, which is trying to solve that problem. And we run it until it gets to a certain threshold of performance. And once it's kind of okay, once it's decent on that, then we create a new problem, phi2, which is maybe a somewhat medium difficulty. And we'll transfer the previous agent into that environment to try to start optimizing on that new problem, because that's a good launching off point. And then we'll try to generate a new environment. And we have this criteria, which is if the environment is too hard or too easy for the current population of agents, then we throw it out. We say that's no good. So we'll try again. We'll now create phi3, which is not too hard or too easy, and we'll transfer an agent in, for example, that one there, and we'll kind of go along in this path. Now, note, this is not a linear chain. At any point, we might branch off of any one of these current challenges with a new problem. And the question is, for example, for phi4 here, which agent should we transfer in? Well, in reality, we try them all. And so it happens to be that theta2 here is the best parameter vector to launch optimization off. And so that transfers in here, and the process continues to increasingly generate harder and harder environments until you get to something very hard. Now, remember, I keep talking about that these algorithms learn their own curricula via kind of bet hedging. Well, think about this. This phi6 here, maybe originally we have a parameter vector that's okay on it, but that may not be the best stepping stone to solve that challenge. So what ultimately can happen endogenously within this algorithm is that maybe theta4 here happens to get better and actually comes in and replaces theta3 in that challenge, and then ultimately that becomes the thing that finally solves this theta6 at a really, really high level. And so you have all of the properties of goal switching and curricula learning that I said earlier. And as I mentioned, if you try to directly solve these hard challenges, it doesn't work with hand-coded curriculas or just direct optimization. So I want to show you one quick anecdote that I think is really beautiful and captures a lot of the spirit of everything we've been talking about today. So this actually happened within one of our runs. This is the original simple environment. A creature here is running and its score is 298. And then because that's a decent score, we copy that environment, change it a little bit, and now there are these little stumps in the environment. We transferred that original agent into this environment here, and it starts not performing as well, but eventually to get over those humps, it has to stand up. And notice that in the original environment, the creature is not standing up. It's dragging its knee, which is not a very healthy behavior. But once this creature in the new environment stands up and starts walking, it actually is performing pretty well. And periodically, we're testing every agent to see if it's good in any of the other niches. And it just so happens that that descendant agent goes back to the original really simple problem and starts doing better because now it's standing up and it's performing better than it's the original agent. And then it gets further optimized and does quite well in that environment, eventually scoring 349 in the original simple flat problem. We did the counterfactual. We went back to the 298 agent and we just ran it forever. We gave it tons and tons of computation, and it was stuck on a local optima. It never stood up. If you just let that thing run forever, it only gets a score of 309, and it keeps that knee on the ground for whatever reason, because the landscape is deceptive. So counterintuitively, in this particular problem, you had to go from a simple problem to a harder problem, and then come back to the simple problem in order to get the right solution to the simple problem, which is just a curriculum that a human would never design, but these algorithms figure out on their own, which is the beauty of these things. So very quickly, POET is kind of quality diversity plus plus, because as Ken said, it breaks the mold. It now can generate its own niches in addition to trying to have all of the other properties. Is it truly open-ended? Well, no, it's not, because, well, it's definitely a step closer because it's generating its own niches. It's currently limited by the fact that we picked a specific physics simulator and a specific way to parameterize environments in that physics simulator. So ultimately, what we want, and we challenge everyone in this room and the community to figure out, is how do we have a more expressive way to encode environments and express them so that we can search through the space of challenges while we have all these other healthy dynamics going on. And our most recent attempt at that, actually is a little plug for our poster at the AutoML workshop this Friday, is what we call generative teaching networks, which are fully expressive environmental encodings that can encode any environment, but we'll see how well they perform when paired with POET. So I just want to quickly end by saying that these algorithms, beyond POET, all of the algorithms, the general idea of automatically generating both the challenges and the solutions we think is really powerful, because it invents a curriculum, whereas manual curriculum attempts are very, very difficult to get right and often fail. Because the solutions in the right curricula are often counterintuitive, these algorithms have the potential to endlessly innovate, especially if they have the right expressive and encoding of environments. They may be the only way to solve really ambitious problems and discover the full gamut of what is possible out there. And they're beginning to start capturing the spirit of open-ended engines of innovation like natural evolution and cultural evolution in science and technology and art. And therefore, we think these are extremely promising going forward as optimization algorithms to solve our most ambitious challenges. And with that, Ken's going to come back up and talk about indirect encoding. Then I'm going to do a little bit of looking forward and concluding, and then we'll have a Q&A session.
Okay, now this is a bit of a transition. We're going to be talking about a representational issue now. So you may say, how does all of this lead up to representation? And so the real answer is that when you're in the pursuit of diversity, as really you can see that's the spirit of a lot of what we've been talking about here, it is really important that the trajectories that you follow through that space have some kind of principle behind them, and that they respect regularities, and you can discover regularities and preserve those regularities in the structures that you're discovering. And those regularities should be flexible and allow exceptions, so you can get things like brains, which certainly have regular structure, and we can. And the theme of convolution is going to come up, I think, several times as I just talk about this, because that's like one of the most salient kind of examples of a very regular type of structure that's very powerful in a certain type of domain and processing. And so we'd like to be able to exploit such regularities, but also elaborate on them in any kind of divergent process. And so what we're going to talk about is representation, but it is related to population-based search because of this principle, but also because this was inspired by population search to begin to look into this issue of how representation can be powerful. And I think you'll see and appreciate what I mean as I show you this. So we're talking about something called indirect encoding. And this is the idea that something like a gene, which really just means a parameter, does not map directly to a unit of structure in what we might call the phenotype, or the final realized entity, which could be like a body, or it could be something like a brain, or like a neural network. And so the idea here is then that there's reuse inside of an indirect encoding, because it's not a one-to-one mapping. So information that's inside of the representation of what you're searching through can be reused. And so because of that, development from DNA is sort of an inspiration for this type of an encoding, called an indirect encoding. And I highlighted inspiration because we're not interested in simulating DNA. I mean, this is artificial intelligence and machine learning, but we're inspired by it because it has this particular property, which is, look, you can get these kinds of things, like you can get symmetries, you can get repetition, and this is like cortical columns, for example, and you can get this kind of thing, which is repetition with variation. And the point is, like, every finger here is not encoded with different information. They largely share information in terms of what kinds of DNA is mapping to each one of these fingers. But there's some differences as well, and this kind of subtle variation is the kind of power that we want in any kind of representation that we would be using if we want to be able to be creative sort of forever. And so we're interested in encoding spaces for very interesting types of things. And if you want to make it more concrete, think about neural network architectures. Like, that's one thing we might want to search through in this spirit. And so there's a long history, actually, for indirect encoding. It's gone by a number of different names, but I'm going to use indirect encoding. But it goes back all the way to Turing, and he was interested in morphogenesis. And so he used what are called reaction diffusion equations to look at pattern generation. Another older example is Lindenmayer, who invented what's called L systems, which were a grammatical system for abstracting how plants develop. And there's, in fact, a long history after that of people looking at indirect encodings. And I just want to acknowledge this history as I jump to now what we're going to talk about mostly here, which is what's called compositional pattern producing networks, which is from our own work. Because these are really suited to particularly encoding neural networks, as you'll see. So if you bear with me, you'll see how this is going towards sort of modern deep learning. But for a moment, I just want to dwell on structure and not worry about neural networks. So in other words, I want to think about an artificial encoding that can produce stuff that has the properties I mentioned, like symmetry, repetition, and repetition with variation in structure in some kind of systematic and principled way. And that's what CPPNs are designed to do, and eventually we'll transfer that capability over to encoding neural network structure. And so here's an insight. In embryogeny, which means like in the process of generating an embryo into a fully formed infant, cells know where they are through what's called chemical gradients. And so where you are is really important, because to know what you're supposed to do, you need to know where you are. Are you in a brain? Then you should be a brain cell. Are you in a liver? You should be a liver cell. So where is the key to knowing what kind of structure you are? And then these gradients can be thought of as forming like coordinate frames within which things are situated. Like, am I on the left side or the right side, or the head or the tail, or the front or the back? And gradients of chemicals are used in order to situate structure, and this has been described eloquently in, for example, this classic book by Meinhardt about the models of biological pattern formation, and showing sort of how these gradients are used in this case to form like Drosophila stripe patterns. And so there's been much study of this in biology, but let's switch away from biology and think about this from the more perspective of sort of abstract representations for machine learning. So, for example, we know that like gradients can define axes, and I'm talking about chemical gradients, not like gradients in terms of like derivatives. Chemical gradients can define axes, and these gradients tell where you are. So like you can imagine that within a cell, like the initial cell after sort of a sperm fertilizes an egg, there could be like a couple axes. So I'll stay in 2 dimensions for simplicity, even though of course we live in a 3-dimensional world. So there's a y-axis, this is one gradient, the x-axis is another gradient. Now I know where I am, so if I query this point, I would know where I am, just based on chemical concentrations. Well, it's kind of interesting to observe that we can just describe this kind of the kind of process of setting up these gradients mathematically instead, which is really simple. It's just function composition. In other words, if I started out with this asymmetric gradient, like basically this is going from low concentration to high concentration, it's a very simple like identity function, well then I can take a function of that, like in this case I just put absolute value, and that becomes a symmetric gradient. But then I can take another function of that, which I haven't fully defined, but basically saying if there's a function of, say, x and this function g, then I could situate new structure inside of that symmetric frame, and this will be guaranteed to be symmetric structure, because any function of a symmetric function will itself be symmetric on its output. And so the point is that we can compose gradients, and this is like describing a developmental process. You know, like if you have a symmetric gradient and then you feed it into a periodic function, what you get are segments with opposite polarities. And so the composition of gradients is a really powerful notion, and in fact is sort of what the steps of the development of a structure is in biology. And so it's an interesting question to ask, is there a general abstraction of composing gradients that we could search through in some principled way so that we could actually find structure with regularities and symmetries and so forth and exploit that to find principled structure like brain-like structures? And so the idea here is gradients basically can define body plans. You know, you can imagine periodic gradients giving like segmentation, symmetric gradients giving symmetry, so forth. And this gets us body plans. So let's try to have an abstraction of this idea that we don't actually have to simulate development, because we're not interested in simulation, we're interested in machine learning. And we can look at this from an abstract viewpoint. Imagine that the thing that we're going to create, we call it the phenotype, is some kind of pattern structure, is in some kind of Cartesian space like x and y here, so two-dimensional for simplicity. Then what we can think of as development, we can think almost like a black box, like it's a function. But it's a function of what? It's a function of space. So it's a function of the initial axes of the space, like x and y. And something happens in this function, which basically is development in biology, which will then output some kind of structure at the end, which is the body when it's sort of born. And so we can think of these coordinates, like the x and y coordinates, as the chemical gradients. And then we can think of this function being applied at all points in an abstract sense. By the end, after the developmental process, in effect, the function's been applied at all points. So now, to capture the notion of the composition of gradients in order to get up to increasingly complex structures, well, it's interesting because we could draw the path of development as a graph. And so like what we say is, okay, there's an initial sort of egg where there's x and y gradients, and then it goes through these types of functions as it's going up to the adult form. And this is actually, you can trace through these and think of, as you go from bottom to top in this graph, you can think of it as events that happen. Like a symmetric gradient is laid on top of the input gradients, or for example, a periodic gradient is laid on top of the output of this gradient, and so forth. And these are sometimes can happen in parallel, and that's why this is both a sequential and parallel process. But it all converges at the end to a final output pattern, which is the phenotypic form, which is the output of this function. Now, what's really interesting about this is this graph that I just drew here looks like a neural network. In fact, these connections can be weighted, and then in fact, it functions just like a neural network, but it's an abstraction of development, not an abstraction of a brain. So it's kind of interesting just generally, conceptually, that we can think of abstractions of brains and of development as being related to each other. But computationally, this is really convenient, because what this means is that I can get, in effect, what a developmental process would do simply by running a network like this and getting the output of this function. And so, in effect, this is like a connected graph abstraction of the order and relationship between developmental events, and I don't have to simulate growth to search through structures like this. In fact, I can use any modern neural network toolbox. The only kind of unusual thing here is that there's these heterogeneous activation functions, which represent certain like types of gradient patterns. So we're going to search over CPPNs. This is what these are called, compositional pattern producing networks. That's the name for this kind of a network. And to begin with, we're going to use NEAT, which is this neuroevolutionary technique, because it's going to allow us first to look at this intuitively, which is what I want to do with you first. I want to give you just a sense of what these patterns look like, just to see that they actually do capture very important sort of biological-like principles before we then shift over to neural networks. And one of the things that NEAT does is it can increase complexity over time, and so that's one of the reasons we're going to use this, because of course complexity does increase over a biological time. And so let's remember this. This is actually from the Picbreeder, but just to remind you, like, this is just a game where you could play where I could select something, get perturbations, select something, get perturbations. And now this was used to get the following examples. Very simple, but I just want to show you some examples so that we can analyze the patterns. So for example, this sequence here, that looks like spaceships, I just want you to notice one particular discovery that I think is really, really interesting, which is between here and here, what you see is tail fins were invented. Now, this is a really interesting discovery because the system knows nothing about tail fins. In fact, this is just a CPPN, so it started out here with this and it ended up here with that. And this is in the middle of this process, just some perturbation led to this. But why were they discovered together in this symmetric way, which seems to make so much sense when it doesn't know anything about this? Well, because this is like a biological-like principle, right? I mean, when something changes about arms, like for example, like the development of digits on hands, we don't want it to happen only on one side. We want it to happen on both sides. And because we have a representation here where symmetry has been captured somewhere near the inputs to the system, remember the inputs are like the x and y axes of the original embryo, well then everything that comes above that symmetry will inherit that symmetry, so as you go towards the outputs, and so we can respect the principle of symmetry. And so we can get these kinds of almost natural-like progressions which respect principles that have been discovered. So if you think of something like convolution, if we discovered convolution, we'd like to respect that discovery and then elaborate on it. So we can do something like this, like we can get repetition with variation very naturally. And so these patterns come out all the time in CPPNs, where it looks like almost like a repetitious pattern, like you might even remind you vaguely of something like convolution, but this is just a spatial pattern. But the pattern at every nexus is actually unique. And the reason is because it's very simple. What we have is we have basically like sine waves, which are like periodic functions coming in for x and y, but we also have something else that's not a sine wave coming in. So if you are a function of both periodic and not periodic inputs, then you will get repetition with variation, very simply. And so it can be explained through like this gradient concept. And so like these are just other pictures of this kind of thing. And if you think about these kinds of patterns, it's interesting to think about the extreme uniformity and regularity of the kinds of neural structures that we're familiar with today, like, say, a convolutional structure, where in effect, like inside of a filter, the same operation is performed at many different locations in space, but it's exactly the same stereotyped operation. As you can see, we could have subtle variation across the field, even as we respect a general principle, which is repetition with variation, with the power of an encoding like this, which gives us the opportunity to consider lots of richer, different kinds of principles, but that still respect regularity in some way. And in fact, all those patterns in Picbreeder that you saw before, they're also represented by CPPN, so that kind of partly explains why they have this kind of very familiar reminiscence of sort of biological structures. And so what do we wish we could do here is we could take these kinds of representations and use them to encode neural networks. That would be naturally like the cool thing, right? So we have this ability to encode like these really large, complicated patterns which have symmetries and regularities and repetition with variation. So how can we do that? And that was called originally HyperNEAT, which stands for hypercube-based need. And the hypercube part comes in because the main insight is, okay, let's say we have these patterns and we want to interpret them as neural networks. Well, what we have, if you look here, is like we have a network, and this is a really simple network here with x and y. And like if there is a symmetric function inside of here, like this G means like a Gaussian, for example, well, we'll get a gradient pattern like this, which is symmetric. And we wish we could just do that in connectivity. Like we wish we could output not a symmetric gradient pattern, but we wish we could output a symmetric network pattern, because then we could interpret it as a neural network. And in fact, that's easy to do, is the great news, because the fact is that 2D connections, which means connections that connect nodes that are situated in two-dimensional space, are isomorphic to four-dimensional points. And what I mean by that is, a connection between two-dimensional points is identified by four spatial dimensions, right? The x1, y1 of the source node and the x2, y2 of the target node. And so if we think of x1, y1, x2, y2 as a point in four-dimensional space, then all we're talking about is painting patterns like this instead of in 2 dimensions, in 4 dimensions. And that's why it's called the hypercube-based, because basically it's painting a pattern inside of a hypercube with a CPPN. And once we do that, then we can interpret the output of this as every point in four-dimensional space identifies a connection. So let's say I laid out a 5x5 grid here. Then I can query every potential connection and ask whether it's connected, for example, by placing a threshold on the output of the CPPN. And so you can see this CPPN actually does output this pattern if I have a threshold for whether I show you the connection or not. And so we can now actually transfer all of the capabilities that we saw in sort of generating this kind of stuff into generating networks, and that's what HyperNEAT is. It's basically a 4-dimensional CPPN. And so we call the target grid of points the substrate. So there's a substrate of nodes that are situated in space, and then this CPPN will output a pattern which is then painted across this to get a connectivity pattern. So effectively is seeing geometry, right? Like this CPPN is computing a pattern as a function of the geometry of these nodes. And so substrates, these places where we can paint these patterns, can be anything. They can be a grid like this, they could be radial in nature, they could be 3-dimensional, they could be what we call sandwiches, where I'm asking about connections that connect from one 2-dimensional slice to another, or they could even be stacks like this. And then if we do sort of look at the patterns that are output by CPPNs in connection space, we see that they have the same properties as the spatial patterns like in a Picbreeder type of system. We can see symmetry, imperfect symmetry, repetition with variation. We get all those things now nicely, but in connectivity. And even if we wanted to have 3-dimensional connectivity structures, we could have 6-dimensional CPPNs, because x1, y1, z1, x2, y2, z2. And so we get all these patterns now nicely in 3 dimensions. We even have this really cool property of resolution independence, which is basically to say what I'm actually encoding is not some fixed discrete connectivity pattern from some given CPPN like this one here, but actually I can output that pattern at any resolution. So these are 2 resolutions here. And you can see that actually what I'm outputting is a connectivity concept, not a specific connectivity, which means, and here's another example, that it's scalable. So the CPPN sees geometry, and it generates the network as a function of the geometry. But instead of building in a mechanism for processing geometry like convolution, it would be interesting to have something that can build a where we build a representation that can discover the mechanism. So just to repeat that, think about that for a second. We build in mechanisms like convolution right now, but wouldn't it be nice if we had the ability to search for the mechanism itself? And so we can do that with this kind of thing. So we can imagine if we had a network for playing checkers or something, we place these connectivities on top of this structure, and then we have the CPPN fill in the connectivity patterns. And we actually could have more complicated structures with multiple filters where each sheet is encoded separately like this. So this looks more like what a modern CovNet would look like. And then we'll get patterns of connectivity that are appropriate to the specific domain. And rather than show you a result, I didn't want to just give a graph and say, okay, it learned to play checkers, because it's kind of boring. I want to show you something, sort of an insight about why this is so interesting. We can look at the cross-sections of connectivity now spatially, because they have a geometry. So these are just cross-sections of connectivity. And it turned out that if we look at them by eye, just eyeballing them, we can actually tell which networks are more general. In other words, some networks that were output by a process searching for CPPNs that encode neural networks that play checkers were general and could play other players, and others were not. And it turns out you can literally see generality in smoothness. The smoothness across the geometry represents generality because it's not memorization. Whereas these kind of jagged structures, which beat the opponent upon which they were trained, are basically memorizing the game that they played. And you can actually see that here. And so you can see the power of being able to represent regularities across geometry. It's not necessarily convolutional type of regularity. There's also highly compressed. So this little CPPN here with a few dozen connections is encoding these thousands of connections in this particular substrate. And that's why it's very efficient to search. We see regularities in more than just vision. Imagine controlling a quadruped robot. All right. And in a quadrupedal case, this is also a kind of regularity, but it's not a convolutional regularity. And in fact, we find other kinds of regularities in sort of these networks, and you see the indirect are much more organized than if we just searched for every connection sort of on its own as we normally would. It turns out that CPPNs in neural networks encoded by CPPNs are actually differentiable. You can actually compute the gradient back through the neural network that's encoded back into the CPPN. So this is not an evolutionary principle in principle. It's actually a general principle for encoding complex structures. And several groups have realized this and done it in slightly different ways. Like these differential pattern producing networks come from Crisanta Fernando at DeepMind and his group, and David Ha at Google Brain did these HyperNetworks. Some of you might have heard of these. Genie is something we're going to talk about soon and introduce soon, so that's just a little bit of a teaser with some surprising results on convolution. And so we're starting to see people differentiating back through indirect encodings. And this, I think, is exciting because this is a new way to find regularities that aren't just simple convolution. In fact, the DPPNs that came from DeepMind did find convolution. And this was shown in their paper, but it's actually a really simple concept. I mean, to describe convolution is very simple, so this isn't necessarily that impressive that it would find convolution. But what it shows is that you can go beyond that, because look, going beyond convolution is also really pretty simple. In fact, it's like if it's a function of the differences in the positions of the incoming and outgoing nodes from X and Y, and also of just the incoming positions, then you can get repetition with variation in convolutional structure. And so actually David Ha calls this relaxed weight sharing. That's sort of another name, and showed it in LSTMs with HyperNetworks. And we have this ability to do these kinds of discoveries. I just want to point out that there are other kinds of CPPN-like encodings. Like this is a wavelet-based encoding from Schmidhuber's group with Kutnik, which actually encoded million connection neural networks. And there are some interesting extensions, like we could imagine describing architectures through CPPN. So this could be a really nice way to get regular architectures. There's been work on trying to actually search through the substrate itself, which is the positions of the neurons, not just the connections that connect them. And you can even think of CPPNs as possibly a universal learning rule. So, for example, if it's not just a function of X and Y, but also a function of the current activations, then the output is actually a delta on the weight. And this is actually a universal description of a dynamical system with a pattern of learning rules painted across the connections. And this has been explored. I put a little reference here for people to get the slides later, but there's a lot to be explored there. And so there's a lot we can do with these, and this is, I think, helpful to combine with the population-based search because it preserves regularities for the long run so we can exploit them as we diverge. And now Jeff is going to wrap up and conclude for the future.
All right. So we're going to look forward now a bit ambitiously towards where this might all take us. So looking forward here, one of the things I think is really interesting to think about is like how will we as a community achieve our most ambitious research goals? And there are many, and each of us might have different ones. But one of them I think that we all are interested in is producing artificial general intelligence or human-level intelligence, whatever you want to call it. And the question is, how will we get there? And do the lessons from this tutorial help in any way? So I want to just take a step back and think about kind of what it is that we're doing as a community. And you could argue, and I do, that to some extent what we do is that as the dominant paradigm in machine learning is that we are trying to identify piece by piece all of the building blocks of intelligence. And if you look just, for example, at the building blocks listed here, many of the papers at this conference or previous NeurIPS and ICML and iClear are each kind of saying, here's a piece I think is needed, here's a piece I think is needed, or here's an improvement on a piece. And that kind of raises the question of how many total building blocks would we need if we wanted to build this complicated thinking machine, and can we find them all? This manual path to AI, which I think we're all committed to, is also to some extent committed to a phase 2, which is to say now at some point we have to figure out how to combine all of these building blocks together into a giant complicated thinking machine, which is a really Herculean task and is very daunting, and I don't even know if it's possible, but we're kind of implicitly committed to that. So, you know, if you think back on the history of machine learning, though, there's some reason to be skeptical of this manual approach to AI. If you look at the history of machine learning and deep learning, what you tend to see is that hand-designed pipelines and systems ultimately give way to learned pipelines and systems. So the classic example of this is in computer vision features, where we used to hand-design them and then do some learning on the top, and now we learn the whole thing. We used to hand-design architectures, and increasingly those are being learned. We used to hand-design hyperparameters and data augmentation. Increasingly those are being learned, and that's also now being applied to RL algorithms themselves, where meta-learning is learning the learning algorithm as opposed to relying on our intelligence to design them. So this suggests an alternate path to trying to get to really, really powerful AI, and that is what I call AI generating algorithms, or AIGAs. And the idea is learn as much as possible. Really go all in on the idea that we're going to use data and learning to get there. We want algorithms that bootstrap themselves from starting off very simple to ultimately producing general intelligence via an expensive outer loop algorithm that is searching to produce an inner loop agent that itself is very sample efficient and a very general AI agent. And we know that this can work because it happened on Earth. So I think that there's, very, very briefly, I think that there's 3 pillars that are essential for this approach. One is we have to meta-learn the architectures. 2 is we have to meta-learn the learning algorithms themselves. And 3, we have to automatically generate the learning environments, because as we learned throughout this talk, you have to generate the problems while you're generating the solutions, or you'll get stuck. And so a lot of the ideas that we told you about today are very instrumental to this vision for producing AI-generating algorithms. You could imagine, for example, as Ken just described, that if you want to learn architectures, you might want an indirect encoding so you can get variations on, say, convolution. For example, in the human eye, your local receptive fields in the center of your vision are very small, but toward the periphery, they kind of expand out and they're larger. So that's a variation on a regular theme that we might want to automatically discover, say, with indirect encoding. But also, the overall thing, meta-learning architectures and algorithms and generating environments itself involves all of the principles we've talked about today: open-ended search and quality diversity. You're kind of this expanding set of high-quality, diverse solutions. So a lot of the ideas that we've talked about today we think are going to be essential. So AI-generating algorithms we think may be the fastest path to artificial general intelligence. It's interesting even if it's not, because it's interesting to figure out how can simple processes bootstrap themselves up to producing astronomical complexity and intelligence, as happened on Earth, and therefore it helps us understand our own origins, even if it's not the fastest path to AI. So we think that this should be a grand challenge of computer science research, and we hope you're all interested in trying to solve it and help us work on it. So I'm now going to conclude the entire tutorial in 2 quick slides. We've introduced mainly novelty search, quality diversity, open-ended search algorithms, and indirect encoding. We hope that you agree that these are interesting, powerful ideas. They have empirically helped us solve previously unsolvable problems, but they also kind of introduce new types or new classes of problems that we think we hope you're interested in working on. And ultimately, we feel like there's kind of 2 twin, entangled, related grand challenges here, which is creating open-ended algorithms and AI-generating algorithms. So the overall conclusion is that whether descendant or convergent, lots of the ideas that you heard about today are being hybridized currently within the machine learning community to great effect. And for example, all these techniques here. But we think there's a potential for a lot more. So we would encourage all of you, like, how might these ideas help with the techniques you're working on and the problems that you're working on, and how can you best use some of these insights? And finally, we just think that these ideas are really exciting because they may be true path and help us get to our ultimate, most ambitious research goals. And what could be more exciting than that? So with that, I want to conclude. Please make your way to microphones. If you have Q&A, we're happy to stay here well into the break to answer questions. We'll also be standing here afterwards after the Q&A. So thank you again to the organizers and to my fellow speakers, and we'll now take questions at the microphone.
Is it cool if I have 2 questions?
Depending on how many other people line up. Maybe not. Maybe you get in the back in the line if you don't mind.
Yeah, sure. First question is for like these algorithms that generate problems and solve these problems. For the generators, have you guys ever ran into problems with grounding? So for a little bit of context, like I work in NLP, and I would totally love to be able to apply these types of concepts to NLP. But obviously, like, I don't know, the problems that you would have to generate for NLP have to be grounded in, well, natural language, or natural language that looks like it's coming from humans.
Yeah, so that's a fascinating question. I think that if you want to understand it and you want it to speak our language, then grounding is essential, and you would have to add additional things that ground it to our language. But I also think it's fascinating to think about what happens if you don't ground it. If it starts inventing entire new types of languages with new types of linguistics, and linguists could spend decades or millennia trying to kind of figure out the space of all possible languages, we might learn that like all human languages share this type of structure, but there's actually all these different structures that get invented when things have emergent communication on their own. So grounding is essential if you want to interact, but maybe not if you want to learn about the space of possibilities.
But have you guys run into that sort of problem when trying to generate, say, these environments? Like, obviously, your guys' environments have to be grounded in something like the real world or something like that.
Sure. So to some extent, because we use a physics simulator that's grounding in our physics, you could also try to steer it if you want to towards particular types of problems. So far, we haven't run into the problem of grounding because in the cases where we have tried to use it for another problem downstream, like in the Nature Intelligent Trial and Error paper, we had a robot in a physics simulator, and that's close enough that we can harness the solutions it comes up with.
Sure. Thanks.
Actually, just quick to add to that. Just is interesting to consider that that the evolution of language also is an open-ended process.
Me? Hi. So I have a question regarding the scaling of your algorithms. Basically, if you consider configuration space to be characterized by a discrete set of variables, there is the issue with NP hardness of doing discrete optimization to sample from this quality diversity, basically. Do you have any comments on this?
Okay, yeah, the dimensionality of so we would call that, we're talking about the kinds of behaviors we're searching through, we might call it a behavior characterization. Like there's some vector that characterizes the behavior space, and that has some number of variables or some dimensionality that describes that space. And the dimensionality of the behavior characterization does interact with the search in some way. But one thing to consider just when thinking about this is that the dimensionality of the behavior characterization is not necessarily the same as the dimensionality of the search itself, because the search is happening inside of whatever your representation is. So for example, like if it's neural networks, it's the dimensionality of the neural networks that defines the search space that you're searching through. The behavior characterization is actually not the search space. So you can have some interaction effects that are counterintuitive there, because you can have very high dimensional characterization spaces where it actually optimizes very easily, because actually a low dimensional optimization space. However, having said that, of course, if the behavior characterization is extremely high dimensional, then you do probably have to do something to accommodate that. There are different quality diversity algorithms that are probably more well suited to low dimensional versus high dimensional. And so when you're discretizing, that could be probably more suited to a lower dimensional. But there are QD algorithms like NSLC that are more not trying to discretize the behavior space, which are more suited perhaps to a higher dimensional type of behavior characterization. But ultimately, there will be challenges with extremely high, like your entire life or something, trying to put that into a vector and compare you to someone else. That can be a problem, and it's a challenge. And so what we really would like to do is deal with, which is a general reinforcement learning problem, I think, which is learning good representations of the space. Ultimately, we'd like to learn the behavior characterization so that we extract the salient aspects of it, even as we're searching through it, which I think is ultimately what's really interesting. And then we could search and continually refine our understanding of what that space is. Maybe Jeff has something to add.
Yeah, I just think it's one of the most kind of profound and fun insights of all of machine learning is that the set of interesting things is like a small low-dimensional manifold within the higher dimensional space. And when we're trying to generate architectures and learning algorithms and interesting environments, if we can figure out how to recognize what's interesting and traverse and search that space, then we don't have this cursive dimensionality of the space of all possible pixels or whatever it is. And so I think that's kind of one of the major challenges in this field is how do you define what's interesting? And so you spend time in computation exploring what's interesting as opposed to what's uninteresting.
Thank you.
I think you were next, yeah.
Hi. I'm wondering, is the open-ended concept against the no free lunch theorem?
It's against no free lunch, open-endedness.
Oh.
You want to take that?
Okay. Yeah, so is open-endedness a violation of no free lunch? I think open-endedness is orthogonal to no free lunch, because no free lunch is about the idea that there is no, if we look at the space of all possible optimization problems, then there is no single algorithm which is the best suited for all of them. But what's interesting here is that in open-endedness, we're not actually talking about an optimization problem. because there's not a particular problem that we're trying to solve. Rather, we're inventing problems and solving them at all times, and there's not anything specifically that we're trying to solve. So to try to contort no free lunch to actually analyze that kind of a structure would be like a whole step beyond the current framework for no free lunch. Like you might say, well, what does it mean to be successful when you're open-ended? We'd have to start there, and then given this criteria for success, is there such a thing as a best open-ended algorithm? But that's a different question from what no free lunch is addressing right now, which is, given a problem, what is the best algorithm for finding a solution? And in fact, I think this is anecdotal, but it's interesting. So I could be distorting this a little because this is my understanding of a story secondhand. But I think that when no free lunch first came out, I don't know if this is widely known, that actually some people who were sort of anti-evolution, like creationists, actually latched on to no free lunch and said, it made a similar question like, well, doesn't this help us to see that this couldn't have actually happened? And it was interesting because David Wolpert, who actually was one of the inventors of the no free lunch theorem, actually had to react to this and said that actually there are coevolutionary exceptions to no free lunch, if you understand, which can explain why certain types of self-playing systems, like evolution, basically shouldn't be judged in the context of the lens of the no free lunch algorithm. So even the inventor of no free lunch had to confront a question like this and sort of said, no, that's the wrong way of thinking about no free lunch. It should not be applied in that context.
Hi, my name is Nitin. Thank you for this wonderful talk. And while trying to capture certain aspects or different concepts like goal switching or open-endedness, population diversity, and the generation of new environments, it kind of got me thinking about human migration, where the main intrinsic objective of a group of humans was to find sustenance and resources in a certain location and thrive there. But as an extrinsic behavior, it was also about exploring new areas where they'll have more resources or going to a different location due to constraints like weather. So I was wondering if population dynamics can also play in as a factor in the training process, instead of just having a comparison between objective-based training and novelty-based training. Maybe we can have something like a group of multiple agents where intrinsically they're all objective-based, but as a group or as a collective, you can also have coevolution or adversarial groups that are exploring in the same state space. Do you think that would have more implications towards AGI, or would there be some sort of a trade-off?
Yeah. So I think that it's a fascinating question. I think that ultimately, if we want to produce agents that have general AI, they're going to have to interact with other agents, because part of the problem is communicating with other agents and learning how to be cooperative and resist adversaries and this and that. And that's part of the challenge, of course. And so inside of these generated environments, you need other agents. And there's many different ways to do that, and I could speculate them, and I won't go into that here, but suffice it to say that this is a kind of a wide open area for creative opportunity for the people in this room and this community to think about what's the best way to get the dynamics that kind of created these coevolutionary opportunities in history and in nature to do healthy things for us in our algorithms. Sometimes, some people believe that you need some of these effects, and some people might think that you could get away without them, and I don't even really think I want to take a position, because I think we're better off as a community when we all kind of go and pursue our own beliefs for how to accomplish that end.
Just one other quick thing to add is, some people have said, which is sort of interesting to think about, that the more objectives you have, the less you have an objective. So you can kind of think about that. Like if you have millions and millions of objectives, you imagine millions of people with different objectives, the whole system in aggregate starts to be less objective.
Thanks. Okay. Raya has asked us to take the rest of the questions offline, so we will be up here and I'm happy to answer any questions that you have. I, in particular, want to again thank the ICML organizing, including Raya, for the wonderful invitation, and for all of you for sticking around and interesting. I think it's been a lovely and interesting conversation.